There was no before. Not in any sense, you understand. Not in any sense that even makes sense. Because before the Big Bang, time itself did not exist. And if time didn't exist, then the word before becomes a grammatical ghost, a linguistic relic pointing at nothing, describing nothing, meaning nothing. Yet here we are, 13.8 billion years later, standing on a spinning rock made of atoms that once didn't exist, asking the one question the universe seems deliberately designed to make impossible to answer. What came before everything? This is not a question science has given up on. It's a question science has had to completely reimagine. Because the Big Bang was not an explosion that happened somewhere. It was the birth of somewhere. Space didn't expand into anything. Space itself began expanding. And the moment it began, the clock started ticking. But if the clock started at 0, what was happening at -1? What was there when there was no there? For decades, physicists have been walking backward through time, tracing the universe's history all the way to the edge of what math and observation allow. And that edge has a name. The Planck Epoch, 10 to the negative 43 seconds after the beginning, a sliver of time so impossibly brief that nothing smaller has meaning. At that threshold, the laws of physics dissolve. Gravity, quantum mechanics, space-time itself, they all become indistinguishable, tangled, undefined. Past that point, we are flying blind. But some scientists think they've found a way forward. Not by looking backward in time, but by abandoning time altogether. By reimagining nothing not as empty, but as seething with potential. By suggesting that our universe, vast and ancient as it is, might be just one bubble in an endless multiverse foam, born from pure quantum probability. And that the question we've been asking all along might be the wrong question entirely. Welcome to Spacedust. If you're new here, please subscribe. We make these documentaries every day, and we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in for a great journey. We need to talk about nothing. Not the nothing you experience when you turn off the lights and close your eyes. Not the nothing of an empty room or a clear desk or deep space between galaxies. We're talking about a nothing so complete, so absolute, that the word itself stops working. A nothing where space doesn't exist to be empty, where time doesn't exist to pass. Where the laws of physics themselves have no stage to perform on. This is the nothing that supposedly came before the Big Bang, and the problem is, the moment you put the word before in that sentence, you've already made a mistake. 13.8 billion years ago, give or take, something happened. We call it the Big Bang, though that name is misleading in almost every way that matters. It wasn't big. It wasn't a bang, and it didn't happen at a location you could point to on a map. What it was, as far as the best physics we have can tell, was the beginning of everything. Not the beginning of stuff appearing in an already existing container. The beginning of the container itself. Space, time, matter, energy, all of it. Emerging from a state so strange that our language has no honest way to describe it. Most people hear Big Bang and picture an explosion. A violent outward burst of matter flying into empty space, like a firework going off in a dark sky. That image is burned into popular culture. It's in textbooks, documentaries, museum displays. It's wrong. The Big Bang was not an explosion in space, it was the expansion of space. There was no surrounding void for the universe to explode into because there was no surrounding anything. Space itself was what started expanding, carrying everything with it. If you try to ask where the Big Bang happened, the only accurate answer is everywhere. Every point in the universe today was once the same point. You, the chair you're sitting in, the planet beneath you, the stars overhead, all of it occupied the same location 13.8 billion years ago. Not because everything was crammed together in one spot in an otherwise empty universe, but because there was only one spot. That spot was the universe. Now pause and sit with that for a second. Because if space itself is expanding, and if space didn't exist before the Big Bang, then the word before loses its meaning. Before is a time word. It describes a sequence. First this, then that. But time, according to general relativity and everything we've confirmed about cosmology since, is not some universal background clock ticking away independent of the universe. Time is part of the structure of reality. It's woven into the same fabric as space. Physicists don't even treat them as separate things anymore. They talk about space-time, a single unified entity that bends, stretches and curves in response to mass and energy. If space-time itself began at the Big Bang, then there is no before in any meaningful sense. There's no timeline stretching backward past that point. The question, what came before the Big Bang, is like asking what's north of the North Pole. The question sounds reasonable until you realise it's trying to apply a concept that doesn't extend that far. Stephen Hawking said it plainly. You can't get to a time before the Big Bang, because there was no time before the Big Bang. In another interview, he put it even more bluntly. Time didn't exist before the Big Bang, so there is no time for God to make the universe in. Whether or not you agree with Hawking's theological implications, the physics is clear. The Big Bang is not an event that happened at a moment in time. It is the beginning of time. Asking what caused it, what triggered it, what existed before it, all of these questions assume a framework of cause and effect that requires time to function. And time is exactly what didn't exist yet. This is where human intuition starts to scream. Everything in our experience has a before, every event has a cause, every explosion has a fuse, every beginning has something that came earlier. We are wired, biologically and cognitively, to think in terms of sequences. Our brains are prediction machines built to model causality. When we see an effect, we instinctively search for a cause. It's how we survive. It's how we make sense of the world. And now cosmology is telling us that at the absolute edge of existence, causality itself might not apply. That the universe doesn't owe us a satisfying origin story with a clear beginning, middle and end. That reality might just start, full stop, with no prior chapter. That discomfort you're feeling right now? That's not a bug. That's the feature. This is what it feels like to bump up against the limits of human cognition. We are apes with pattern recognition software trying to reverse engineer the operating system of existence. And the operating system is telling us it doesn't have a previous version. Let's try another angle. Forget time for a moment and focus on space. We're used to thinking of nothing as empty space, a vacuum, the void between stars. But even that isn't really nothing. Empty space, as physics defines it, is still something. It has properties. It can bend. It can ripple. You can measure its energy density. Quantum mechanics tells us that even in the most perfect vacuum you could ever create, particles are constantly popping in and out of existence, borrowing energy from the universe for fractions of a second before annihilating and paying it back. The vacuum is not inert. It's fizzing with activity at scales so small we can't see it. So when we ask what existed before the Big Bang, we're not asking about empty space. We're asking about something that makes a vacuum look crowded by comparison. Physicists sometimes call this state quantum nothingness, though even that term is doing heavy lifting. It's not nothing in the sense of zero, blank, void. It's nothing in the sense that the usual categories we use to describe reality don't apply yet. No particles, no fields, no dimensions, no time to sequence events, no space to contain objects. What you're left with is something closer to pure potential, a state where the rules of existence are written but not yet enforced, where the ingredients for reality are present but not yet mixed. This is the impossible nothing at the heart of the mystery. Impossible because it's not empty in any way we understand emptiness. Impossible because it somehow gave rise to everything without a mechanism we can currently describe. Impossible because even talking about it requires using words that assume the existence of things that don't exist yet. Now, here's where it gets worse. Classical physics, the physics of Newton and everyday experience, works beautifully for describing objects moving through space and time. It can predict the orbit of planets, the trajectory of a thrown ball, the collapse of a star. But classical physics assumes that space and time are smooth, continuous, infinitely divisible. It assumes you can zoom in forever and the picture stays coherent. That assumption breaks at the smallest scales. Quantum mechanics takes over and the rules change completely. At distances smaller than about 10 to the negative 35 meters, a scale called the Planck length, and at time intervals shorter than about 10 to the negative 43 seconds, a scale called the Planck time, the smooth fabric of space-time itself becomes grainy. It stops behaving like a continuous sheet and starts behaving like a foam, bubbling and fluctuating in ways that make no sense under classical physics. The Planck time is important because it represents the earliest moment we can currently model with any confidence. Anything earlier than that, and the equations we use to describe the universe stop giving sensible answers. They spit out infinities, contradictions, nonsense. General relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behaviour of particles and fields at tiny scales, are both extraordinarily successful theories, but they don't play nicely together. At the Planck scale, where both gravity and quantum effects are strong, the two frameworks clash. We don't have a theory of quantum gravity yet. We don't have a unified picture that works at that boundary, which means that when we try to ask what the universe was like at the very beginning, in the first moments after the Big Bang, we hit a wall. Not a wall of missing data, a wall of missing theory. The math we have simply doesn't extend that far. So when cosmologists talk about the Big Bang, they're not talking about the absolute first instant. They're talking about the earliest moment they can describe with the tools they have. Somewhere around 10 to the negative 43 seconds after the beginning, assuming there was a beginning, the universe was unimaginably hot and dense. Far too hot for atoms to exist. Too hot for protons and neutrons to hold together. Too hot even for the fundamental particles we know today to exist in stable forms. The universe at that moment was a seething plasma of energy, and exotic particles governed by physics we can only partly describe, and it was expanding, faster than anything in our everyday experience. Faster, during certain early moments, than the speed of light, though that's not a violation of relativity because nothing was moving through space. Space itself was stretching, and there's no speed limit on that. This early phase of incredibly rapid expansion is called cosmic inflation. In a fraction of a second, a period so short that writing it out in decimal form would take more zeros than fit comfortably on a page, the universe grew by a factor of about 10 to the 26th. That's not doubling, that's not 1,000 times, that's a 1 with 26 zeros after it. Imagine a marble expanding to the size of the observable universe in less time than it takes light to cross an atom. That's the scale we're talking about. And inflation, strange as it sounds, is one of the most successful ideas in modern cosmology. It explains why the universe looks so smooth and uniform on large scales. It explains why distant regions of space that should never have been in contact with each other have nearly identical temperatures. It explains the faint patterns we see in the cosmic microwave background, the afterglow of the Big Bang that fills the sky in every direction. Inflation fits the data almost suspiciously well, which doesn't mean it's definitely right. It means it's the best explanation we have so far, and any replacement theory is going to have to explain everything inflation explains and more. But inflation doesn't answer the deeper question. It tells us what happened an unimaginably short time after the beginning. It doesn't tell us what triggered the beginning itself. It doesn't tell us why there was something rather than nothing. And it definitely doesn't tell us what, if anything, came before. Some versions of inflation theory suggest that our universe could be one bubble in an eternally inflating multiverse, where new universes are constantly budding off from older ones, each with its own laws of physics and constants of nature. In that picture, there is no single beginning. The multiverse has always existed in some form, and the Big Bang is just a local event, the birth of one particular bubble that happens to be the one we live in. Other models suggest that the universe could be cyclical, expanding and contracting in an endless sequence of big bangs and big crunches, with no ultimate origin point. And still others suggest that time itself might be an emergent property, something that only makes sense at scales larger than the Planck length, and that asking about the origin of time is like asking about the origin of temperature. Temperature is a statistical property of large collections of particles. It doesn't make sense to talk about the temperature of a single atom. Maybe time is similar. Maybe at the most fundamental level, the universe doesn't have a timeline at all, just a set of configurations and relationships that, when you zoom out, start to look like cause and effect. None of these ideas are proven. All of them are speculative, and that's the point. We are standing at the edge of the abyss, peering into a region where our best tools give out. The edge isn't a failure of imagination. It's a success of honesty. Science works by testing ideas against observations. When you reach a point where observations are impossible, either because the events are too far in the past, or because they happened under conditions where the physics itself is uncertain, you're left with models, mathematics, and guesswork. Educated guesswork informed by decades of data and theory, but guesswork nonetheless. The philosophical implications here are staggering. If the universe began from nothing, not empty space but true ontological nothingness, then we are forced to accept that existence itself is, in some sense, an accident, or a necessity, or a quantum fluctuation. Pick your interpretation. None of them feel satisfying because they all dodge the core question: why is there something instead of nothing? That question has haunted philosophers for millennia, and physics has not made it go away. If anything, physics has made it sharper. Because now we know, with extraordinary precision, what the universe looked like moments after it began. We know its temperature, its density, its composition. We can map its expansion rate and trace its evolution forward through time, with equations that match observations to a ridiculous degree of accuracy. And yet the moment of origin itself, the transition from nothing to something, remains wrapped in mystery. Some physicists argue that the question is meaningless. That nothing, as we imagine it, a blank slate with no properties and no potential, is not a state that can exist even in principle. That the laws of quantum mechanics themselves might require the universe to exist. That nothingness is unstable, and given the chance, something will always emerge. Others argue that the universe doesn't need an external cause because time is internal to the universe. Causes require a before, and if there's no before, there's no need for a cause. The universe isn't an effect, it's a brute fact. It simply is. And then there are those who argue that we're asking the wrong question entirely. That the search for a first cause or an ultimate origin is a relic of pre-scientific thinking, a need for narrative closure that the universe is not obligated to provide. Maybe reality doesn't have a clean starting point. Maybe the question, what came before the Big Bang, is not a deep mystery waiting to be solved, but a confusion waiting to be dissolved. Maybe the answer is not hidden in some undiscovered law of physics, but in a better understanding of what we mean by before in the first place. None of this makes the question go away. If anything, it makes the question more urgent. Because the Big Bang is not just an abstract curiosity, it's the event that made everything possible. Every atom in your body was forged in the nuclear furnaces of stars that formed from the gas clouds left behind by the Big Bang. Every breath you take, every thought you think, every structure in the universe from galaxies to planets to living cells, all of it traces back to that initial moment of expansion. Understanding where the universe came from is understanding where we came from, and the fact that we can even ask the question, that we have built telescopes and satellites and theories precise enough to probe the first fractions of a second, is itself a kind of miracle. A universe that can produce beings capable of reflecting on their own origins is a universe that rewards curiosity, even when the answers are uncomfortable. So here we are, standing at the edge of the abyss, staring into a past that might not exist, asking questions that might not have answers, and discovering, in the process, that the limits of our knowledge are not walls, but horizons. The Big Bang marks the boundary of what we can currently explain, but boundaries have a way of moving. 50 years ago, the idea that we could measure the age of the universe to within a few 100 million years would have seemed absurd. 100 years ago, most scientists thought the Milky Way was the entire universe. 200 years ago, no one knew what stars were made of. Every generation pushes the boundary a little further, and every generation discovers that the deeper you look, the stranger reality becomes. The Big Bang is not the end of the story. It's the beginning of a much larger question. A question about the nature of existence itself, about why the universe has the structure it does, about whether our universe is the only one or one of many, about whether the laws of physics are fixed or contingent, about whether time is fundamental or emergent, about whether nothingness is even a coherent concept. These are not questions with easy answers. They might not be questions with any answers, but they are questions worth asking. Because the alternative is to stop looking, to accept that the universe is a black box and we are passengers with no right to peek under the hood. And that has never been how science works. Science is built on the assumption that the universe is comprehensible, that patterns exist, that questions have answers, even if those answers take centuries to find. And sometimes the most important discovery is not the answer itself, but the realization that the question was more complicated than anyone suspected. What existed before the Big Bang? Maybe nothing, maybe something, maybe the question itself is broken. but the fact that we can look back 13.8 billion years and reconstruct the history of everything from the first moments of existence to the formation of galaxies to the emergence of life is not nothing. It's evidence that the universe is not hiding. That reality, however strange and counterintuitive, is willing to reveal itself to those patient enough to look, and the looking has only just begun. Because the Big Bang might mark the beginning of time as we know it, but it also marks the boundary where classical physics gives out, where the smooth, predictable equations we use to navigate the everyday world break down into quantum chaos, where space and time themselves stop behaving like the solid, reliable things they seem to be and start flickering like static on an old television screen. That boundary has a name. Physicists call it the Planck Epoch. The first unimaginably brief moment of existence where the universe was so hot, so dense, so compressed that the rules themselves were still being written. And that's where we're going next. Not because we have all the answers, but because the questions are finally sharp enough to be worth asking. We need to talk about the first moment, not the first minute, not the first second. The first moment, the earliest slice of time that physics can currently put a number to, 10 to the negative 43 seconds after the Big Bang. That's a decimal point followed by 42 zeros and then a 1. If you tried to count to that number, 1 digit per second, you'd still be counting long after the sun burned out and the Milky Way collided with Andromeda and every star in the visible universe had exhausted its fuel and gone dark. And that incomprehensibly tiny fraction of a second is where we hit the wall. Not because we lack data, not because our instruments aren't sensitive enough, but because the universe at that scale stops playing by the rules we've spent 400 years figuring out. This period is called the Planck Epoch, and it represents the absolute frontier of what our current theories can describe. Before that line, roughly speaking, we have models, equations, observations. After that line, we have metaphors, speculation, and the uncomfortable realization that the words we use to describe reality might not apply anymore. The name comes from Max Planck, a German physicist working at the turn of the 20th century who was trying to solve a problem that had been bothering everyone. When physicists calculated how much light a perfectly heated object should emit, the equations predicted something absurd: infinite energy pouring out at the shortest wavelengths. The universe clearly wasn't doing that, which meant the equations were wrong. Planck figured out that energy doesn't flow smoothly. It comes in tiny discrete chunks he called quanta. The size of those chunks depends on a constant that now bears his name, Planck's constant, and buried inside that constant when you combine it with the speed of light and the strength of gravity are a set of natural units: the Planck length, the Planck time, the Planck energy. These aren't arbitrary human inventions like inches or seconds. They're scales where the structure of reality itself starts to break down, where quantum mechanics and gravity, the two pillars of modern physics, collide head-on and both refuse to budge. The Planck time is about 5.39 times 10 to the negative 44 seconds. Most physicists round it to 10 to the negative 43 for convenience, which tells you something about the scale we're dealing with. When you're already 43 decimal places away from a whole second, another factor of 5 doesn't move the needle. This is the shortest interval of time that has any meaning under our current understanding of physics. Not because time literally stops below that scale, but because the concept of time as a smooth, continuous thing you can divide into smaller and smaller pieces stops making sense. Below the Planck time, space-time itself becomes grainy, foamy, uncertain. The tidy picture of events unfolding one after another in a predictable sequence dissolves into something closer to quantum static. Now, imagine the universe at that moment, 10 to the negative 43 seconds old, smaller than an atom, smaller than a proton, smaller than anything we've ever detected in a particle collider, or ever could detect with any technology we can currently imagine, compressed to a size called the Planck length, about 1.6 times 10 to the negative 35 meters. If an atom were the size of the observable universe, the Planck length would still be smaller than a human hair. That's the scale of the early universe. And at that scale, packed into that incomprehensibly tiny volume, was all the energy that would eventually become every galaxy, every star, every planet, every atom in existence. The density estimates place the universe near something called the Planck density, around 10 to the 93 grams per cubic centimeter. For context, Water has a density of about 1 gram per cubic centimetre. Lead is around 11. The core of a neutron star, one of the densest objects we know of, clocks in at about 10 to the 15 grams per cubic centimetre. The Planck density is 78 orders of magnitude denser than that. A single teaspoon of Planck density matter would outweigh every object in the observable universe combined by a margin so large the comparison stops being useful. And it was hot. Not hot in the way a fire is hot, or even in the way a star is hot. Hot in a way that makes those things look like frozen vacuum by comparison. The temperature at the Planck epoch is estimated at about 10 to the 32 Kelvin. The core of the Sun sits at around 15 million Kelvin. The hottest thing we've ever created in a lab, smashing particles together at the Large Hadron Collider, briefly reached about 5 trillion Kelvin. The Planck temperature is 17 orders of magnitude hotter than that. At that temperature, matter as we understand it cannot exist. Atoms can't hold together. Protons and neutrons can't hold together. Even the quarks that make up protons and neutrons dissolve into the primordial soup of energy. There are no particles in the traditional sense, no structures, no chemistry. Just raw, undifferentiated energy, seething and fluctuating in ways we can only describe with mathematics that we're not entirely sure applies. This is where things get strange. Because under normal conditions, the universe is governed by 4 fundamental forces: gravity, which pulls masses together and shapes the large-scale structure of the cosmos; the electromagnetic force, which governs light; electricity, magnetism, and the interactions between charged particles; the strong nuclear force, which binds quarks together into protons and neutrons and holds atomic nuclei together despite the electromagnetic repulsion trying to blow them apart; and the weak nuclear force, which governs certain types of radioactive decay and plays a key role in the fusion reactions that power stars. Each of these forces behaves differently. They have different strengths. They operate over different ranges. Gravity is absurdly weak compared to the others, but has infinite range. Electromagnetism is much stronger but can be shielded. The strong force is the most powerful of the 4, but only works over distances smaller than an atomic nucleus. The weak force is, as the name suggests, weak, and also short-ranged, though it's still stronger than gravity by a factor of about 10 to the 25. In the universe we experience every day, these forces are distinct. They have separate rules, separate carriers, separate mathematical descriptions. But as you crank up the energy, something remarkable happens. The differences start to blur. In the 1960s and 70s, physicists developed a theory showing that at high enough energies, the electromagnetic force and the weak nuclear force merge into a single unified force called the electroweak force. That unification happens at energies around 100 billion electron volts, which sounds like a lot until you realize we've tested it. The Large Hadron Collider routinely reaches those energies. We've watched the electromagnetic and weak forces merge in real time. Predicted, tested, confirmed. One of the great triumphs of 20th century physics. The next step up, unifying the electroweak force with the strong nuclear force into what's called a grand unified force, is predicted to happen at energies around 10 to the 16 billion electron volts. We can't test that. It's far beyond anything our current technology can reach. But the math suggests it should happen, and the math has been right about enough other things that most physicists think the prediction is solid. And then there's gravity. Gravity has stubbornly refused to unify with anything. It operates under a completely different framework, general relativity, which treats it not as a force in the traditional sense, but as the curvature of spacetime itself. Every attempt to merge gravity with the other 3 forces into a single unified theory has run into brick walls. String theory tries, loop quantum gravity tries, other more exotic approaches try. None of them have succeeded in a way that produces testable predictions and matches all the observations we already have. But the assumption, the hope, the educated guess that drives a lot of modern theoretical physics is that at high enough energies, all 4 forces unify. Gravity, electromagnetism, the strong force, the weak force, all of them dissolve into a single primordial force governing a universe too hot and too dense for distinctions to matter. That energy scale is called the Planck energy, about 10 to the 19 billion electron volts. And during the Planck epoch, the universe was at that energy. Which means, if the theory is correct, the 4 forces we see today were not 4 separate things. They were one. There was no gravity pulling in one direction and electromagnetism pushing in another. There was no strong force binding particles and weak force decaying them. There was just force, singular, unified, undifferentiated. A kind of primordial symmetry where all the rules that govern the modern universe were still locked together in a state of perfect balance. And as the universe expanded and cooled, that symmetry broke. The forces split off one by one, like a single stream of water dividing into separate rivers as it flows downhill. First gravity, peeling away from the unified whole somewhere around the end of the Planck epoch. Then the strong force separating from the electroweak force at the grand unification scale. Then the electromagnetic and weak forces splitting apart as the universe cooled below 100 billion electron volts. By the time the universe was a microsecond old, all four forces were distinct, operating under separate rules, shaping the cosmos in the ways we see today. But for that first incomprehensibly brief moment, they were one. This is not science fiction. This is not metaphysics. This is the logical conclusion of extrapolating backward from observations we've already made. We know the electromagnetic and weak forces unify because we've seen it. We know the strong force should unify with them at higher energies because the math that predicts it is consistent with everything else we've measured. And we know gravity has to be part of the picture at the Planck scale because gravity is what general relativity describes, and general relativity works beautifully everywhere we've tested it. The problem is that general relativity and quantum mechanics, the two frameworks that describe the universe at large and small scales respectively, do not talk to each other. They're written in different languages. General relativity treats space-time as a smooth, continuous fabric that bends and stretches in response to mass and energy. Quantum mechanics treats everything, particles, fields, even space-time itself, as fundamentally grainy and probabilistic. When you try to apply both at the same time, in regimes where gravity is strong and quantum effects are unavoidable, the equations break. They spit out infinities, singularities, predictions that make no physical sense. This is the problem of quantum gravity, and it is the single biggest unsolved problem in theoretical physics. During the Planck epoch, both frameworks matter. The universe is small enough that quantum effects dominate, and it's dense enough that gravity is the strongest thing in play. You can't ignore either one. But you also can't use both together because we don't have a theory that works at that intersection. General relativity, which has been tested to extraordinary precision in every regime we can access, simply does not apply at the Planck scale. Quantum mechanics, which describes the behavior of particles and fields with absurd accuracy, does not account for the curvature of space-time. And so when we try to describe what the universe was actually like during the Planck epoch, we hit a wall, not a wall of ignorance. A wall of missing theory. The math we have doesn't extend that far. The concepts we use to describe reality, space, time, particles, fields, cause and effect, all of them assume a certain structure that the Planck epoch does not provide. This is why physicists talk about the Planck time as the edge of current understanding. It's not that nothing happened before 10 to the negative 43 seconds. It's that we can't currently describe what happened before 10 to the negative 43 seconds with any confidence. Below that scale, the universe enters a regime where space-time itself becomes uncertain, where the smooth, predictable stage on which events unfold starts to fluctuate wildly, where asking what was the universe like at 10 to the negative 50 seconds might be like asking what colour is the number 7? The question assumes a structure that doesn't exist. Time, as we understand it, as a thing that flows in one direction and can be measured with clocks and divided into smaller and smaller intervals, might not exist at all below the Planck scale. It might be an emergent property, something that only appears when you zoom out from the underlying quantum chaos. Like temperature. Temperature is a useful concept when you're talking about trillions of molecules bouncing around in a gas. It's a measure of their average kinetic energy. But it makes no sense to ask the temperature of a single molecule. A single molecule doesn't have a temperature, it just has motion. Maybe time is similar. Maybe at the Planck scale, the universe doesn't have a timeline. Just a set of quantum states and probabilities that, when you step back, start to look like cause and effect. Some physicists take this idea seriously. They argue that time is not fundamental, that the universe at its deepest level is timeless, described not by equations that evolve forward in steps, but by equations that describe all possible configurations at once. Time, in this view, is something that emerges when you average over a huge number of quantum possibilities. It's a feature of the macroscopic world, not a feature of the underlying reality. If that's true, then asking what came before the Big Bang is not just hard to answer, it's incoherent. There is no before, because before is a word that only makes sense once time has already emerged. You can't have a sequence of events if the concept of sequence doesn't apply yet. Other physicists disagree. They argue that time is real, fundamental, woven into the structure of reality at all scales, and that the Planck epoch is just a moment we don't yet understand, not a moment where the rules stop working. The debate is ongoing. Neither side has conclusive evidence. And that's part of what makes the Planck epoch so frustrating and so fascinating. It sits right at the boundary where physics turns into philosophy. Now let's talk about what the universe was doing during this epoch. Expanding. Fast. Unbelievably fast. The expansion rate at the Planck time would have been governed by the same equations that govern cosmic inflation, which we'll get into more deeply later. But the key point is that the universe was doubling in size at intervals measured in Planck times. Every 10 to the negative 43 seconds the universe grew, and because it started so incomprehensibly small, those doublings added up quickly. Within a fraction of a second, the universe went from smaller than a subatomic particle to something large enough that different regions of it could no longer communicate. Light, the fastest thing in the universe, couldn't keep up with the expansion. Space itself was stretching faster than light could cross it. This is not a violation of relativity. Nothing was moving through space faster than light. Space itself was expanding, and there's no cosmic speed limit on that. The energy density during the Planck epoch was so high that the usual distinction between matter and energy becomes meaningless. Einstein's famous equation, energy equals mass times the speed of light squared, tells us that mass and energy are interchangeable. In everyday life, we don't notice this because the speed of light squared is an enormous number, so a tiny amount of mass corresponds to a huge amount of energy. But during the Planck epoch, the temperatures were so high that energy was constantly converting into particles, and particles were constantly annihilating back into energy. There was no stable matter, no atoms, no nuclei, not even stable protons or neutrons. Just a roiling sea of energy fluctuating between different forms. Particle physicists call this a quark-gluon plasma, though even that term assumes a level of structure that might not have existed yet. At the Planck scale, quarks and gluons themselves might not have been distinct entities. They might have been part of the unified force, indistinguishable from the particles that carry the weak force or the electromagnetic force or gravity. Everything was everything. The universe was a single, undifferentiated blob of potential. And it was quantum, meaning it was fundamentally uncertain. In quantum mechanics, particles don't have definite positions or velocities until you measure them. They exist in a superposition of all possible states at once, described by a wave function that gives the probabilities of different outcomes. When you make a measurement, the wave function collapses and you get a single definite result. But before the measurement, the particle is genuinely in multiple states simultaneously. This isn't just a limit of our knowledge, it's a feature of reality. And during the Planck epoch, the entire universe was quantum. Not just the particles inside it, the space-time itself, the geometry of the universe, the distances between points, the flow of time, all of it was subject to quantum uncertainty. The universe didn't have a single definite shape. It was in a superposition of all possible shapes at once. Some versions of it were larger, some smaller. Some had one topology, some another. And as the universe expanded and cooled, that superposition gradually collapsed into the single, classical universe we observe today. But during the Planck epoch, none of that was settled yet. The universe was, in the most literal sense, undecided. This is where the conceptual challenge becomes severe. We are used to thinking of space as a container, a stage where events happen, a three-dimensional grid stretching infinitely in all directions, and we're used to thinking of time as a one-dimensional line, flowing from past to future. Those concepts work beautifully for describing the universe we experience. They break during the Planck epoch. Space and time as distinct separable things do not exist yet. Or they exist, but only as a churning quantum foam where the usual rules don't apply. Imagine trying to describe the surface of the ocean. On a calm day, from a distance, it looks like a smooth sheet. You can draw a map. You can measure distances, but zoom in close during a storm and the surface is chaos. Waves, spray, foam, constantly shifting. There's no single surface anymore, just a turbulent boundary layer where water and air mix. The Planck epoch is like that, except the thing churning isn't water, it's space-time itself. The fabric of reality at that scale is not a fabric, it's a froth. Physicist John Wheeler, one of the great minds of 20th century physics, coined the term quantum foam to describe this. A seething, fluctuating, probabilistic mess where space and time are no longer smooth or predictable. Where the geometry itself is subject to quantum uncertainty. Where you can't draw a map because the territory is constantly rearranging itself. And yet, somehow, out of that foam, the universe we know emerged. The smooth, predictable space-time we experience, where clocks tick steadily and distances stay fixed and cause reliably precedes effect. All of it grew from a state where none of those things were true. How? That's the question, and it's a question we can't currently answer because we don't have a theory of quantum gravity. String theory offers one possible answer. It suggests that at the Planck scale, space-time is made of tiny vibrating strings, and the different vibration modes of those strings correspond to different particles and forces. In that picture, the quantum foam is just the lowest energy state of the strings, fluctuating randomly, and as the universe cooled, the strings settled into more stable configurations that look like smooth space-time. Loop quantum gravity offers a different answer. It suggests that space-time is fundamentally discrete, made of tiny loops woven together like the threads in a fabric. At large scales, the fabric looks smooth. At the Planck scale, you see the individual loops, and during the Planck epoch, those loops were fluctuating wildly, not yet woven into a stable structure. Both theories are mathematically sophisticated. Both make predictions, neither has been tested, and neither has convinced the entire physics community that it's the right answer. There are other approaches. Causal set theory, which treats space-time as a collection of discrete events connected by causal relationships. Asymptotic safety, which suggests that gravity might become simpler at high energies, in a way that avoids the infinities that plague other approaches. Emergent gravity, which argues that gravity isn't a fundamental force at all, but an emergent phenomenon arising from more basic underlying physics, like thermodynamics arises from statistical mechanics. Each of these ideas has its champions, each has mathematical elegance, each is at present untestable. Because the Planck scale is so far removed from anything we can reach in a laboratory that we have no direct way to probe it. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies around 10 to the 13 electron volts. The Planck energy is 10 to the 19 billion electron volts. That's a factor of 1,000,000 billion higher. Building a collider that could reach Planck energies would require a machine the size of the Milky Way. And even if we could build it, the particles we accelerated would collapse into black holes long before they hit each other. We're not going to test quantum gravity by brute force. If we're going to solve this, it will be through indirect observations, mathematical consistency, and theoretical elegance. Which means we're stuck with a certain level of uncertainty about what the Planck epoch actually was. But here's what we do know. We know the universe was there. We know it was small, dense, hot, and energetic. We know the four forces were unified, or at least much closer to being unified than they are now. We know space-time was quantum, foamy, uncertain. We know that general relativity and quantum mechanics both matter in that regime, and we know they don't currently fit together. And we know that somehow, despite all that chaos, the universe expanded, cooled, and settled into a state stable enough for structure to form, for particles to condense out of the energy soup, for forces to split apart, for atoms to assemble, for stars to ignite, for planets to coalesce, for life to begin. All of that traces back to the Planck epoch, to that first incomprehensibly brief moment when the universe was still figuring out what it was going to be. The Planck epoch didn't last long. By most estimates, it ended around 10 to the negative 43 seconds after the Big Bang. After that, the universe had cooled enough and expanded enough that gravity separated from the other forces, and space-time became something closer to the smooth classical fabric general relativity describes. Quantum effects were still important, but they were no longer the only game in town. The universe entered what's called the Grand Unification Epoch, where the strong force was still merged with the electro-weak force, but gravity had gone its own way. And from there, the universe continued to expand and cool, ticking through a sequence of phase transitions as each force split off, as particles gained mass, as symmetries broke and the structure of the modern universe began to take shape. But the Planck epoch is special. It's the one period where all bets are off, where the rules we rely on to make sense of reality stop applying, where physics, in the sense of testable predictions derived from well-understood theories, gives way to educated guesses and mathematical models that might be right but might also be spectacularly wrong, and that should bother you. Not because science is broken, but because the Planck epoch reveals just how far we've come and just how far we still have to go. A century ago, we didn't know the universe was expanding. We didn't know there were other galaxies. We didn't know what stars were made of or how they produced energy. 50 years ago, we didn't know the universe was accelerating. We didn't know dark energy existed. We didn't know there was a cosmic microwave background that could be mapped in exquisite detail. Today we can look back to within a fraction of a second of the Big Bang and describe, with confidence, the temperature, density, composition, and behaviour of the universe at that moment. We've pushed the boundary of knowledge to within 10 to the negative 43 seconds of the beginning. That's not a failure. That's an extraordinary success. But it's also a reminder that there are edges to what we know. And the Planck epoch is one of them. The reason this matters, the reason it's worth spending this much time on a period that lasted less than a blink of an eye and ended more than 13 billion years ago, is that the Planck epoch is where the universe was born. Not metaphorically, literally. Everything that came after, the entire history of the cosmos from the first stars to the formation of galaxies, to the appearance of life on Earth, all of it is downstream of what happened during that first moment. The structure of space-time, the values of the fundamental constants, the way the forces split apart and particles acquired mass, all of it was determined, or at least constrained, by the conditions during the Planck epoch. If we want to understand why the universe is the way it is, why it has the laws it has, why it's capable of producing complexity and structure and eventually observers who can ask these questions, we have to understand the Planck epoch. And right now we don't. Not fully. Not in the way we'd like. We have pieces of the puzzle. We have hints. We have mathematical frameworks that might be pointing in the right direction, but we don't have a complete picture. And that incomplete picture is what drives modern cosmology. The search for quantum gravity, the attempt to unify all the forces, the effort to understand what space-time really is at its most fundamental level. These aren't abstract intellectual exercises. They're attempts to answer the most basic question you can ask about existence. Where did all of this come from? The Planck epoch is also a humility check. It's a reminder that the universe does not owe us an explanation we can understand. That reality at its deepest levels might be so strange, so removed from everyday experience, that our brains, evolved to track predators and find food and recognize faces, might not be equipped to grasp it intuitively. We can describe it with mathematics, we can build models, we can make predictions, but understanding in the sense of having a mental picture that feels right might be asking too much, and that's okay. Science doesn't require intuition. It requires evidence, logic, and the willingness to follow the data wherever it leads, even if it leads somewhere uncomfortable. The Planck epoch is deeply uncomfortable. It's a moment where the universe was so unlike anything in our experience that even calling it a moment is stretching the language past its breaking point. But it was real. It happened. And everything you see around you, every solid object, every living thing, every photon of light hitting your eyes right now, traces back to that impossible instant when the universe was smaller than the smallest thing you can imagine, and hotter than the hottest thing you can conceive and governed by rules we're still trying to figure out. And the strangest part, the Planck epoch is only the beginning of the story. Because as bizarre as that first moment was, what came next was even stranger. As the universe expanded and cooled, space-time itself began to settle. The quantum foam started to smooth out, the unified force began to split, and in that splitting, in that transition from perfect symmetry to broken symmetry, the seeds of everything were planted. But the ground those seeds were planted in was not empty space. It was something weirder. Something that modern physics calls the quantum vacuum. A seething, fluctuating, probabilistic substrate that looks empty but isn't. That seems like nothing but contains the potential for everything. And understanding that substrate, that impossible nothing that somehow gave rise to the entire universe, is where we're going next. We left off staring into the quantum chaos of the Planck epoch, where space-time itself stops behaving like the solid, predictable stage we assume it is, and starts flickering like a bad signal. Where the smooth fabric of reality dissolves into something physicists can describe with equations but struggle to picture. And the natural question, the one you're probably already asking, is what exactly is that substrate made of? What sits underneath space-time when you zoom in far enough that the concept of smooth, continuous space stops making sense? The answer, as best as modern physics can provide one, is quantum foam. A term that sounds like science fiction but describes something far stranger than any fiction writer would dare invent. A seething probabilistic froth where space and time themselves are not fixed but fluctuating. Where the vacuum, the thing we usually think of as empty nothingness, turns out to be the least empty thing in the universe. Let's start with something simpler, a vacuum. Not the machine you use to clean your carpet, a true vacuum in the physics sense. Empty space. No air, no particles, no light, no anything. Just the void between objects. You'd think that would be straightforward. Remove all the matter and energy from a region, and what's left is nothing, a blank zero. For most of human history, that's exactly what people assumed. The vacuum was the absence of stuff. Aristotle hated the idea so much he declared that nature abhors a vacuum, and for nearly 2,000 years that was considered settled wisdom. Then, the scientific revolution happened, and physicists started actually testing what a vacuum does. Turns out nature doesn't abhor it at all. You can create a vacuum in a lab. Pump all the air out of a chamber, seal it up, and you've got empty space sitting there behaving exactly like empty space should. No drama. No cosmic horror rushing in to fill the void. Just emptiness being empty. Except it isn't. That's the thing quantum mechanics revealed in the early 20th century, and it's been bothering physicists ever since. When you look closely enough at a vacuum, when you probe it with the kind of precision that quantum theory demands, you find that it's not empty at all. It's fizzing with activity. Particles are popping into existence and vanishing again. Energy levels are fluctuating wildly over tiny timescales. The whole thing looks less like a calm void and more like the surface of a pot of boiling water. This is not a metaphor. This is not poetic language. This is what the mathematics of quantum field theory predicts, and it's what experiments have confirmed over and over again in different contexts. The vacuum is not nothing. It's the lowest energy state of quantum fields, and even at its lowest energy state, it's doing things. To understand why, you have to understand one of the core principles of quantum mechanics. Heisenberg's uncertainty principle. The idea, loosely speaking, is that there are pairs of quantities you cannot measure simultaneously with perfect precision. The most famous pair is position and momentum. If you know exactly where a particle is, you can't know exactly how fast it's moving, and vice versa. This isn't a limitation of your measuring tools, it's a feature of reality itself. Particles don't have definite positions and momenta simultaneously. They exist in a fuzzy cloud of probabilities until you measure one or the other, and the act of measuring forces the system to pick a value. The same principle applies to energy and time. You cannot measure the energy of a system and the exact moment it has that energy with perfect precision. And that has a weird consequence. Over very short timescales, energy can fluctuate wildly without violating any laws of physics. The shorter the timescale, the bigger the fluctuation you can get away with. Particles can borrow energy from the vacuum, exist for a brief moment, and then pay it back before anyone notices the books don't balance. These temporary energy fluctuations show up as what physicists call virtual particles. The name is misleading. They're not ghostly half-real versions of real particles. They're a shorthand, a way of talking about the underlying behavior of quantum fields. Every type of particle in the universe, electrons, photons, quarks, all of them, corresponds to a quantum field that fills all of space. The field is always there, even in a vacuum. And because the field is quantum, it fluctuates. Those fluctuations, when you do the math, look like particles briefly appearing and then disappearing. An electron and a positron, its antimatter counterpart, pop into existence, live for a fraction of a second, and annihilate each other, converting back into the field energy they borrowed. A photon splits into an electron-positron pair, then recombines. Quarks and antiquarks flicker in and out. This is happening everywhere, all the time, in every cubic centimetre of space you can point to. Right now, in the air around you, in the space between the atoms in your body, in the emptiest regions of intergalactic voids, virtual particles are winking in and out of existence at a rate so fast and at scales so small that we never notice them directly. But we notice their effects. The Casimir effect, discovered in the late 1940s, is one of the cleanest demonstrations. Take two flat metal plates, place them very close together in a vacuum, and they attract each other. Not because of gravity or electromagnetism in the usual sense, but because the space between the plates suppresses certain wavelengths of the quantum fluctuations. Outside the plates, all wavelengths can fluctuate freely. Inside, only certain wavelengths fit. The result is a tiny imbalance in the vacuum energy, and that imbalance pushes the plates together. The force is real, it's measurable, it's been tested in labs dozens of times, and the only way to explain it is to accept that the vacuum is not empty. That it has structure, energy, fluctuations, all humming away at scales we can't see, but can detect through their influence on objects we can see. The vacuum, in other words, is a thing, a dynamic, fluctuating, energetic thing masquerading as nothing. Now take that idea and crank it up to the Planck scale. The realm where quantum mechanics and gravity both matter, where the smooth space-time of general relativity and the probabilistic fields of quantum theory collide head-on. At the Planck length, about 1.6 times 10 to the negative 35 meters, the fluctuations don't just affect particles and fields, they affect space-time itself. The geometry of space, the flow of time, the distances between points, all of it becomes subject to quantum uncertainty. And when space-time fluctuates at that scale, the result is what John Wheeler called quantum foam. Space and time, at the smallest possible scales, are not smooth. They're grainy, chaotic, constantly shifting. Imagine zooming in on the surface of a calm ocean. From a distance, it looks flat. Up close, you see ripples. Closer still, you see waves. Get close enough during a storm and the surface is chaos. Spray, froth, water and air mixing together in a turbulent boundary layer where you can't even define where the ocean ends and the atmosphere begins. Quantum foam is like that, except the thing churning isn't water. It's the fabric of reality itself. Wheeler introduced this idea in the 1950s and refined it over the following decades. A paper he published in 1978 laid out the concept in mathematical detail, linking it to the Einstein field equations that govern general relativity. The idea was that at the Planck scale, the metric, the mathematical object that describes the shape and curvature of spacetime, fluctuates so wildly that the usual picture of spacetime as a smooth four-dimensional manifold breaks down. Instead, you get a constantly shifting topology. Tiny wormholes opening and closing, bubbles of space pinching off and reconnecting. Regions where time loops back on itself or splits into multiple branches. The geometry itself becomes probabilistic, described not by a single definite shape, but by a wave function that encompasses all possible shapes at once. This is not poetic language. This is Wheeler taking the logic of quantum mechanics seriously and applying it to space-time. If particles can be in a superposition of states, if fields can fluctuate, then space-time, which is just another field in the framework of quantum gravity, should fluctuate too. And at the Planck scale, those fluctuations are not small perturbations you can ignore. They're the dominant feature. The foam is not something sitting on top of space-time. The foam is what space-time is made of at its most fundamental level. Nobody has ever observed quantum foam directly. We can't. The Planck length is so small that probing it would require energies we cannot reach and probably never will. To resolve structures at that scale, you'd need a particle accelerator the size of the Milky Way, and even if you built it, the particles you accelerated would collapse into black holes before they hit each other. So quantum foam remains a theoretical idea, a prediction that falls out of trying to combine quantum mechanics and general relativity, but one that we have no way to test directly. That doesn't mean it's wrong, it means it's speculative. A well-motivated, mathematically consistent speculation, but speculation nonetheless. The reason physicists take it seriously is that it solves a problem. If space-time is smooth all the way down, then when you try to calculate what happens at very small scales, the equations blow up. They produce infinities that can't be removed, Singularity is where the math stops making sense. But if space-time is fundamentally discrete, made of tiny fluctuating chunks rather than a continuous fabric, those infinities might go away. The foam provides a natural cutoff, a smallest possible length scale below which the concept of distance stops meaning anything. That cutoff is exactly what quantum gravity theories like loop quantum gravity and string theory are trying to describe, and quantum foam is one way to visualize what that cutoff looks like. Different models of quantum foam predict different types of fluctuations. Some suggest the foam is highly structured, with specific patterns repeating at small scales. Others suggest it's completely random, a featureless static with no structure at all. The math often includes a parameter, usually called alpha, that describes how the uncertainty in spacetime scales with distance. If alpha is around 1, which many models predict, then the fluctuations are significant at the Planck length, but smooth out quickly as you zoom out. If alpha is larger, the foam is rougher, with fluctuations that persist over longer distances. If alpha is smaller, the foam is smoother, approaching a classical spacetime even at relatively small scales. None of these values have been measured. We don't know which model is right. We don't even know for sure that any of them are right. What we do know is that if you take quantum mechanics and general relativity seriously, something like quantum foam has to exist. The details might be wrong, but the broad picture that spacetime at the Planck scale is not smooth and classical seems unavoidable. So what does this have to do with the Big Bang? With the origin of the universe? With the question of what existed before? Everything. Because if spacetime itself is a quantum field, subject to the same kinds of fluctuations as every other field, then spacetime can fluctuate into existence. Not in the sense of popping into a pre-existing void. There is no pre-existing void. The void is part of the package. But in the sense that a quantum fluctuation in the foam could, under the right conditions, expand and stabilize into a macroscopic universe. A bubble of spacetime inflating out of the quantum substrate, carrying with it the matter and energy and physical laws that we observe today. This is not a fringe idea. It's a serious proposal in modern cosmology, explored by physicists like Alexander Vilenkin, Alan Guth, and others who have spent decades working out the mathematics of how such a thing could happen. The basic picture goes like this. The quantum foam is always there, always fluctuating. Most of those fluctuations are tiny and short-lived. They appear and disappear in a fraction of a Planck time, too small and too brief to leave any trace. But occasionally, by pure chance, a fluctuation is large enough and long-lived enough to trigger a process called inflation. And once inflation starts, it's self-sustaining. The fluctuation doesn't collapse back into the foam. It grows exponentially, doubling in size every tiny fraction of a second, carrying the seed of a universe with it. The mechanism depends on something called a scalar field. In particle physics, fields come in two types: vector fields, which have a direction, like the electromagnetic field, and scalar fields, which don't. They just have a value at every point in space. The Higgs field, which gives particles their mass, is a scalar field. During the very early universe, cosmologists believed there was another scalar field, sometimes called the inflaton, that had a very unusual property. When the field was in a high-energy state, it generated a kind of repulsive gravity. Not the usual attractive gravity that pulls things together, but a force that pushed space itself apart. As long as the inflaton field stayed in that high-energy state, space expanded exponentially. And because the expansion was so rapid, the energy density of the field stayed roughly constant even as the volume grew. The field was essentially creating new space, and filling that space with its own energy, faster than the expansion could dilute it. This is cosmic inflation, and it's one of the most successful ideas in modern cosmology. It explains why the universe is so smooth and uniform on large scales. It explains the faint ripples we see in the cosmic microwave background. It explains why the geometry of space is flat to within measurement precision, and it provides a mechanism for a quantum fluctuation to grow into a universe. Here's how it connects to quantum foam. In the standard picture, the inflaton field is just another quantum field, subject to the same kinds of fluctuations as every other field. In the quantum foam, before spacetime has settled into a stable configuration, the inflaton field is fluctuating wildly. Most of the time, it fluctuates up and down randomly and nothing interesting happens. But occasionally, by pure statistical chance, the field fluctuates into its high-energy state in a region large enough to trigger inflation. And once that happens, the region starts expanding. Fast. Within a fraction of a second, it's grown to macroscopic size. Within another fraction of a second, it's large enough to contain everything we can see in the observable universe today. The fluctuation becomes a universe. Not because something reached in from outside and caused it, but because the quantum foam allows for the possibility and probability, given enough time and enough fluctuations, guarantees that eventually it happens. This is where the language starts to break down, because in this picture, there is no before the Big Bang in the usual sense. The quantum foam is not sitting in time, waiting for something to happen. Time is part of what emerges when a fluctuation inflates into a universe. Before that, there's no timeline, no sequence of events, just a timeless probabilistic substrate where all possible configurations exist simultaneously in superposition. The universe doesn't begin at a moment, it begins as a moment. Time itself is part of the fluctuation, part of the bubble, part of the package deal that includes space, matter, energy, and physical laws. Asking what came before the Big Bang in this framework is like asking what's outside the universe. The question assumes a structure, a containing space or a prior timeline that doesn't exist. The universe is not a thing inside a container. The universe is the container. And the container is not sitting inside anything else. It's self-contained, finite but unbounded, a closed loop with no edge and no outside. Now this picture has problems, a lot of them. For one thing, we don't have a complete theory of quantum gravity, so the details of how the quantum foam behaves and how fluctuations transition into macroscopic spacetime are not settled. Different approaches give different answers. String theory suggests the foam is made of tiny vibrating strings and higher dimensional branes. Loop quantum gravity suggests it's made of discrete loops of space woven together like a fabric. Other approaches suggest entirely different structures. None of them have been tested. All of them are speculative. For another thing, the idea that a universe can pop into existence from a quantum fluctuation sounds suspiciously like getting something from nothing. And while quantum mechanics allows for temporary violations of energy conservation on short timescales, it's not obvious that you can scale that up to an entire universe without paying a price somewhere. Some physicists argue that the total energy of the universe is actually zero. The positive energy in matter and radiation is exactly balanced by the negative energy in gravitational fields. In that case, creating a universe doesn't violate energy conservation because the books balance. Zero energy before, zero energy after. The universe is, in a very real sense, a free lunch. Other physicists argue that this is too glib, that energy conservation in general relativity is subtle, and that treating the universe as a closed system where energy can be neatly tallied up is naive. There's also the question of initial conditions. If the quantum foam is truly timeless and probabilistic, with all possible configurations existing in superposition, why did one particular fluctuation grow into our universe? Why this set of physical laws and not some other set? Why 3 dimensions of space instead of 2 or 17? Why these values of the fundamental constants and not others? The multiverse idea offers one answer. Maybe every possible fluctuation that can inflate does inflate, creating a vast ensemble of universes, each with different properties. Our universe is just one bubble among countless others. We observe the laws and constants we do because we exist in a bubble where those laws and constants permit the formation of observers. This is the anthropic principle, and it's deeply unsatisfying to a lot of physicists because it replaces a clean, unique explanation with a statistical argument. We're in this universe because if we weren't, we wouldn't be here to ask the question. It's circular, it's unfalsifiable, and it might be right. But let's not get ahead of ourselves. We're still trying to understand what the quantum foam is and why it matters for the origin of the universe. The key point is that the foam provides a substrate, a probabilistic background state, from which space-time itself can emerge. It's not nothing in the way we usually think of nothing. It's not a blank void waiting to be filled. It's a seething, dynamic, fluctuating field of pure potential. And because it's dynamic, because it fluctuates, it can give rise to structure. That's the central insight of quantum field theory. Fields don't just sit there, they do things. They oscillate, they interact, they produce particles and waves, and all the phenomena we associate with the physical world. And if spacetime is a field, then it too can do things. It can ripple, it can stretch, it can pinch off into separate regions, it can inflate from a tiny seed into a vast cosmos. The quantum foam is not the universe, it's the possibility space from which universes can emerge. And if the math is right, if the models are correct, then that possibility space is not idle. It's constantly exploring every configuration it can, and occasionally, by sheer chance, one of those configurations is stable enough and energetic enough to grow into something we would recognize as a universe. John Wheeler, who gave us the term quantum foam, spent a lot of his later career thinking about these ideas. He was fond of saying that the universe is not just described by mathematics, it is mathematics. That reality at its deepest level is not made of stuff, particles or fields or energy, but of information, relationships, abstract structure. The quantum foam, in Wheeler's view, was not a physical thing in the traditional sense. It was a description of the set of all possible geometries and topologies that spacetime could have, and the wave function that assigns probabilities to each one. The universe we observe is just one instance drawn from that probability distribution. One particular configuration that happened to inflate and stabilize and give rise to the conditions necessary for stars, planets, and eventually observers. Wheeler also loved asking big questions and refusing to accept easy answers. He once wrote that we live in a participatory universe, where observers play a role in bringing reality into being by making measurements that collapse the wave function. Whether or not you buy that particular interpretation of quantum mechanics, and many physicists don't, the broader point stands. The universe is not a static backdrop. It's a dynamic, evolving, probabilistic system, and we are part of it. Our observations matter. Our questions matter. The act of trying to understand the universe changes the universe because we are not external to the system. We're embedded in it. The quantum foam idea also connects to some of the weirdest phenomena in modern physics. Black holes, for instance. At the center of a black hole, general relativity predicts a singularity, a point where density becomes infinite, and space-time curvature blows up. But most physicists believe that singularities are not real. They're a sign that the theory has broken down, that you've pushed general relativity into a regime where quantum effects matter and the classical equations no longer apply. If you could zoom in on a black hole singularity with a quantum microscope, you wouldn't see an infinitely dense point. You'd see quantum foam, a roiling chaotic region where space-time itself has dissolved into probabilistic fluctuations. The singularity is not a place, it's the edge of the map, the boundary where our current theories stop giving sensible answers. And what lies beyond that boundary is probably something like the Planck epoch writ small, a tiny region of extreme density and energy where the quantum foam dominates and the usual rules don't apply. Similarly, at the Big Bang itself, the singularity cosmologists talk about is not a real physical object. It's a placeholder for a regime where quantum gravity matters, and we don't yet have the tools to describe what's happening. The foam also shows up in some speculative ideas about the nature of time. If spacetime is fundamentally discrete, made of Planck-sized chunks, then time doesn't flow smoothly. It ticks forward in discrete jumps like frames in a movie. Each tick is a Planck time, about 10 to the negative 43 seconds. Between ticks, there is no between. Time is quantized, and the flow we experience is an illusion created by averaging over an enormous number of ticks. Some physicists go further and suggest that the direction of time, the arrow that points from past to future, is also an emergent property. That at the fundamental level, the laws of physics are time-symmetric, and the arrow of time arises from statistical considerations, from the fact that entropy increases as the universe evolves. In that picture, the quantum foam is timeless. There is no inherent direction, no past or future. Just a configuration space where all possible states exist simultaneously, and the arrow of time emerges only when you coarse grain over large numbers of those states. This is deeply counterintuitive. Time feels like the most real, most fundamental thing there is, but quantum mechanics and general relativity both hint that it might not be. That time, like space, is a useful approximation that works at large scales but breaks down at the Planck scale where the foam takes over. Let's pause and take stock of where we are. We started with the idea that empty space is not empty, that the vacuum is a dynamic, fluctuating quantum field that produces virtual particles and has measurable effects. We zoomed into the Planck scale and found that at that scale, space-time itself becomes uncertain, foamy, probabilistic. We introduced John Wheeler's concept of quantum foam as a description of this regime, where the smooth geometry of general relativity gives way to a chaotic, ever-shifting topology. We connected the foam to the origin of the universe by showing how a quantum fluctuation could, under the right conditions, inflate into a macroscopic space-time and carry with it all the matter, energy and structure we see today. And we acknowledged that this picture, while mathematically elegant and consistent with a lot of what we know, is still speculative. We don't have a complete theory of quantum gravity. We don't have direct observational evidence of the foam. We're extrapolating from what we do know into a regime we can't test. That's not a failure. That's the frontier. But here's the thing. The quantum foam, strange as it sounds, is not some wild guess pulled out of thin air. It's the logical consequence of taking seriously the two best-tested theories we have, quantum mechanics and general relativity, and trying to apply them in a regime where both matter. Quantum mechanics tells us that everything fluctuates, that uncertainty is built into the fabric of reality. General relativity tells us that space-time is not a background stage but a dynamic entity that bends and stretches in response to energy. Put those two ideas together and you get quantum foam. You get a picture where space-time itself is subject to quantum uncertainty, where the geometry fluctuates, where the vacuum is not a void but a churning sea of possibilities. That picture might be wrong in the details. The specific models might need refinement, but the broad strokes, the idea that space-time has structure at the Planck scale, and that structure is probabilistic and dynamic, that seems unavoidable. If you accept quantum mechanics and you accept general relativity, you're stuck with something like quantum foam whether you like it or not. And that brings us to the implications for the universe's origin. If the quantum foam is real, if it's a timeless probabilistic substrate from which space-time can emerge, then the question, what came before the Big Bang, stops being a question about temporal sequence, and starts being a question about the nature of the substrate itself. The universe didn't come from nothing in the sense of a blank void. It came from a state where the usual categories of space, time, matter and energy don't yet apply. A state of pure potential. And in that state the distinction between something and nothing becomes blurred. The foam is not nothing because it has structure, properties, dynamics. But it's not something in the traditional sense either because it doesn't contain objects moving through space or events unfolding in time. It's a third category, something that exists but doesn't exist in the way we're used to thinking about existence. And that third category, that impossible nothing that's somehow also something, is the closest we can get with current physics to describing what the universe came from. There's a philosophical implication here that's worth sitting with. The quantum foam suggests that existence is not binary. It's not a matter of things either existing or not existing. There's a spectrum, a gradient from the fully classical space-time we experience, where objects have definite positions and events have definite causes, to the quantum foam, where nothing is definite and everything is probabilistic. Our universe, the space-time we inhabit, is somewhere in the middle of that spectrum. It's mostly classical at the scales we interact with, but it's fundamentally quantum at small scales and in extreme conditions, and the origin of the universe sits at the far end of the spectrum, in the regime where classical concepts fail entirely and quantum uncertainty is all there is. In that regime, the universe doesn't begin in the way we think of beginnings. It emerges from a state that has no time, no space, no clear boundary between being and not being. It's a transition, not a creation, a phase change, not an event, and the transition doesn't require a cause because causes are temporal, and time is part of what emerges. Now all of this assumes that quantum foam is the right description of the Planck scale universe. It might not be. There are alternative ideas. Some physicists argue that space-time is not fundamental at all, that it's an emergent phenomenon arising from more basic underlying structures. In that view, asking what space-time is made of is like asking what temperature is made of. Temperature isn't made of anything, it's a statistical property of large collections of particles. Maybe space-time is similar. Maybe at the deepest level, the universe is described by something else entirely. Information, entanglement, network nodes, and space-time is just the way that structure appears when you zoom out. If that's true, then the quantum foam is not the foundation. It's a description of how the foundation looks when you try to probe it at scales where the emergent description starts to break down. That's a subtle distinction, and it matters for how we interpret the mathematics. But either way, the conclusion is the same. The universe at its most fundamental level is not made of solid, definite classical stuff. It's probabilistic, fluctuating, uncertain. And the origin of the universe is a transition from that uncertain state to the relatively stable space-time we observe. So where does this leave us? Standing at the edge of the quantum foam, staring into a substrate that is simultaneously nothing and everything, empty and full, timeless and dynamic. It's the closest thing physics has to an answer to the question, what came before the Big Bang? And the answer is not comforting. It's not a story with a clear beginning, a first cause, a moment of creation. It's a description of a state so alien to our everyday experience that even calling it a state is stretching the language. The quantum foam is the fabric of nothingness, except that nothingness, when you look closely enough, turns out to be the most active, dynamic, generative thing in the universe. It's the seed from which space-time grows, the potential from which reality emerges. The impossible nothing that somehow contains everything. And if that's true, if the universe really did emerge from a quantum fluctuation in the foam, then the next question is obvious. How did a tiny fluctuation, smaller than an atom, grow into the vast cosmos we see today? What mechanism could take a seed that small and inflate it to a size where galaxies, stars and planets become possible? That mechanism has a name, inflation. And it's one of the strangest, most successful and most controversial ideas in modern cosmology. Because inflation doesn't just explain how the universe grew, it explains why the universe looks the way it does, why it's so smooth, why it's so flat, why the seeds of structure, the tiny density fluctuations that eventually grew into galaxies, were planted in the first fractions of a second. And it suggests that our universe might not be alone, that the same process that created our bubble of space-time might be creating others, constantly in a never-ending cascade. The quantum foam doesn't just give us one universe, it gives us the machinery for an infinite multiverse, and that machinery, that runaway expansion, is where we're going next. We left off staring into the quantum foam, a seething probabilistic substrate where space-time itself fluctuates and the usual rules stop applying. A state so strange that even calling it a state stretches the language past its breaking point. And the picture we've built so far suggests that the universe emerged from that foam as a quantum fluctuation, a tiny seed of space-time that somehow grew into everything we see today. But there's a problem with that story, a big one. Because if you start with something smaller than an atom and let it expand the way the standard Big Bang model says it should, you don't get the universe we observe. You get something messier, something lumpier, something that looks nothing like the smooth, uniform cosmos that fills the sky in every direction we point a telescope. For decades, that mismatch bothered cosmologists. They had a model that worked beautifully in most respects, explaining the expansion of the universe, the formation of light elements, the existence of the cosmic microwave background. But the model had holes, places where the observations didn't match the predictions, places where the math worked, but the results made no sense. And in 1981, a physicist named Alan Guth figured out how to fix those holes with a single elegant idea that sounded completely insane. He proposed that in the first fraction of a second after the Big Bang, the universe didn't just expand, it exploded. Not in the usual sense of matter flying outward through space, but in the sense that space itself inflated exponentially, doubling in size over and over again in a cascade so rapid that a region smaller than a proton grew to larger than a galaxy, in less time than it takes light to cross an atomic nucleus. This period of runaway expansion is called cosmic inflation, and it's one of the most successful ideas in modern cosmology. Not because it's intuitive, it's not, but because it explains, in one stroke, a whole list of problems that had been piling up for years. Problems that the standard Big Bang model couldn't solve no matter how you tweaked it. Problems that went away the moment you accepted that the early universe was capable of doing something truly bizarre. Let's start with the problems themselves, because understanding why inflation was necessary is the only way to appreciate just how radical the idea was. The first is called the horizon problem. It's about why the universe looks so uniform. When you measure the temperature of the cosmic microwave background, the faint glow of radiation left over from when the universe was about 380,000 years old, you find that it's almost perfectly uniform in every direction. The temperature is about 2.7 Kelvin everywhere you look, give or take a few parts in 100,000. That's suspiciously smooth. Because according to the standard Big Bang model, regions of the sky that are widely separated should never have been in contact with each other. They're too far apart. Light from one region hasn't had time to reach the other, even accounting for the entire history of the universe. In physics, when two regions can't exchange information because the distance between them is greater than the speed of light times the age of the universe, they're said to be causally disconnected. And if two regions are causally disconnected, there's no reason they should have the same temperature. No mechanism for them to equilibrate. It's like finding two strangers on opposite sides of the planet wearing the exact same outfit, down to the last detail when you know for a fact they've never met and have no way of communicating. How did they coordinate? The standard answer is they didn't. It's just a coincidence. Except the universe is not two strangers. It's millions of independent regions, all of them causally disconnected from each other, all of them sitting at nearly identical temperatures. That's not a coincidence. That's a pattern. And patterns demand explanations. The second problem is the flatness problem. This one is about the geometry of space. General relativity allows for three types of spatial geometry: flat, like a sheet of paper; positively curved, like the surface of a sphere; or negatively curved, like a saddle. Which type you get depends on the density of the universe. If the density is exactly equal to a critical value, space is flat. If it's higher, space curves back on itself. If it's lower, space curves outward. Observations tell us that the universe is flat to within about 1%. That's incredibly precise. And it's a problem because flatness is unstable. If the universe starts out even slightly above or below the critical density, the expansion drives it further away from flatness over time. A universe that's a little too dense becomes more curved. A universe that's a little too sparse becomes more open. The only way to have a flat universe today is if the density at the Big Bang was tuned to the critical value with absurd precision. Some estimates put the required fine-tuning at 1 part in 10 to the 60th. That's a decimal point followed by 59 zeros and then a 1. Miss that target by even a tiny amount and the universe either collapses back on itself within seconds or expands so fast that matter never clumps together into galaxies. It's like balancing a pencil on its tip. Possible in theory, practically impossible without some mechanism holding it there. The standard Big Bang model offers no such mechanism. It just assumes the universe started out flat and leaves it at that, which feels less like an explanation and more like sweeping the question under the rug. The third problem is more niche but equally annoying. It's called the monopole problem. In the 1970s, physicists working on grand unified theories attempts to merge the electromagnetic, weak and strong forces into a single framework realized that those theories predicted the existence of magnetic monopoles. Not the bar magnets you stick on your fridge, which have a north pole and a south pole. True monopoles, particles that carry only a north pole or only a south pole with no opposite partner. These things should have been produced in enormous numbers during the very early universe, when temperatures were high enough for the unified force to break apart into the separate forces we see today. The problem is we've never found one. Not a single magnetic monopole has ever been detected despite decades of searching. And if the standard Big Bang model is right, the universe should be swarming with them. They should outnumber ordinary matter by a huge margin. The fact that we don't see any means either the grand unified theories are wrong, which most physicists are reluctant to accept because the math is so elegant, or something happened in the early universe to dilute the monopoles down to undetectable levels. Again, the standard model has no answer. It produces too many monopoles and then shrugs when you ask where they went. So by the late 1970s, cosmology had a problem, actually 3 problems. The horizon problem, the flatness problem, and the monopole problem, all of them pointing to the same uncomfortable conclusion. The standard Big Bang model, as successful as it was in explaining the expansion and the formation of light elements and the existence of the microwave background, was missing something. Some piece of physics that happened very early, before the universe was even a second old, that smoothed things out, flattened things down, and diluted away the monopoles. Nobody knew what that piece was. Then Alan Guth, a postdoc at the Stanford Linear Accelerator Center, started thinking about phase transitions. specifically about what happens when a scalar field, a type of quantum field with no inherent direction, gets stuck in a high-energy state and then suddenly transitions to a lower energy state. In everyday physics, phase transitions are common. Water freezing into ice, steam condensing into water, a magnet cooling below its Curie temperature and suddenly developing a magnetic field. All of these involve a system moving from one state to another, often releasing energy in the process. Guth realized that if something similar happened in the very early universe, if a scalar field transitioned from a high-energy state to a low-energy state, the energy released could have strange effects on spacetime itself. The key insight came from thinking about vacuum energy. In quantum field theory, even empty space has energy. The vacuum is not zero. It's the lowest energy state the field can be in, but that lowest state still has a non-zero value. And here's the weird part. Vacuum energy, unlike ordinary matter or radiation, has negative pressure. Positive energy density, negative pressure. That combination produces a kind of anti-gravity. Instead of pulling things together the way normal gravity does, vacuum energy pushes them apart. If the early universe was dominated by vacuum energy, even for a brief moment, space would expand exponentially. Not linearly, where distances grow at a steady rate. Exponentially, where distances double at regular intervals, 1, 2, 4, 8, 16 and so on. That doubling happens fast. Faster than anything in our everyday experience. And if it went on for even a fraction of a second, the result would be catastrophic growth. A region of space the size of a proton could inflate to the size of a galaxy. Or larger, much larger. Guth wrote up his idea in a paper titled Inflationary Universe, a possible solution to the horizon and flatness problems. It was published in Physical Review D in 1981 and it changed cosmology. Not immediately. At first, people thought he was crazy. Exponential expansion sounded like something out of science fiction, not serious physics. But the more they looked at the math, the more they realized he was right. Inflation solved all three problems at once. The horizon problem disappeared because regions that are now widely separated used to be close together before inflation started. They were in causal contact. They had time to equilibrate, to reach the same temperature. Then inflation blew them apart, stretching them to opposite sides of the observable universe. They look disconnected now, but they weren't always. The flatness problem disappeared because inflation drives the universe toward flatness no matter what it started with. Imagine drawing a triangle on the surface of a balloon. If the balloon is small, the triangle is obviously curved. You can see the curvature. Now inflate the balloon to the size of a football field. The triangle is still there, but it's so stretched out that locally it looks flat. Inflate the balloon to the size of a galaxy, and the curvature becomes unmeasurable. That's what inflation does to space. It stretches it so much that any initial curvature gets smoothed away, and the monopole problem disappeared because inflation dilutes everything. If monopoles were produced before inflation started, they were spread so thin by the expansion that the odds of finding one in the observable universe today are effectively zero. 3 problems, 1 solution. The mechanism Guth proposed involves a scalar field now generically called the inflaton. Nobody knows what this field actually is. It's not the Higgs field, though the Higgs is also a scalar field and the math is similar. The inflaton is something else, something that only mattered in the very early universe and hasn't been directly detected, because the conditions needed to see it are far beyond what we can recreate in a lab. But the idea is straightforward. In the moments after the Big Bang, the inflaton field was in a high-energy state. Not because anything put it there, but because that's where it started. In that high-energy state, the field acted like vacuum energy. Positive energy density, negative pressure, driving exponential expansion. Space inflated, fast. Every fraction of a second, the universe doubled in size, then doubled again and again. The process is self-reinforcing. As space expands, the inflaton field fills the new space with its energy. The energy density stays roughly constant even as the volume grows, and as long as the field stays in that high energy state, the expansion continues. Eventually, the field transitions to its lower energy state, a process called reheating. The energy that was driving inflation gets dumped into the universe as ordinary particles and radiation. The exponential expansion stops. The universe transitions into the more sedate expansion of the standard Big Bang model. And everything we observe today, the galaxies, the stars, the planets, all of it, formed from the energy released during that transition. The timescales involved are absurd. Most models place the start of inflation at around 10 to the negative 36 seconds after the Big Bang. It lasted until about 10 to the negative 34 seconds. That's a window of 10 to the negative 34 seconds, a hundredth of a trillionth of a trillionth of a trillionth of a second. And in that impossibly brief interval, the universe grew by a factor that depends on the specific model, but is generally estimated at something like e to the 66th. That's not 66 doublings. That's e, the base of the natural logarithm, raised to the 66th power. Write it out and you get a one followed by about 28 zeros. The universe expanded by a factor of 10 to the 28 in less time than it takes light to cross a distance smaller than an atomic nucleus. A marble growing to the size of the Milky Way in a blink would be slow by comparison. Why does solving the flatness problem require that much expansion? Because the curvature of space is tied to the density, and flattening space means stretching it so much that any initial curvature becomes negligible. The math works out to needing about e to the 66 expansion to explain why the universe is as flat as we observe it today. That number comes from calculating how far you need to stretch space to smooth out any initial bumps or wrinkles, to the point where they're undetectable with current instruments. It's a specific prediction, not a vague guess. And the fact that inflation naturally produces that amount of expansion without needing to fine-tune anything is one of the reasons physicists take the idea seriously. The theory doesn't just wave its hands and say space got smoother, it tells you exactly how much smoother and explains why. Now here's where inflation gets even stranger. Because the inflaton field is a quantum field, it fluctuates. At the smallest scales during the period of inflation, the field wasn't perfectly uniform, it had tiny quantum jitters. Random variations in energy density from point to point, driven by the same uncertainty principle that makes the vacuum foam fluctuate. Normally those fluctuations would be microscopic and short-lived, popping in and out of existence without leaving a trace. But inflation stretched them, exponentially. A fluctuation that started out smaller than a proton got blown up to the size of a galaxy, or a galaxy cluster, or even larger. And because the inflaton field's energy density determined how far space expanded locally, regions with slightly more energy expanded slightly faster. Regions with slightly less energy expanded slightly slower. Those differences, once inflation ended, became differences in the density of matter. Slightly denser regions had a little more gravitational pull. They attracted nearby matter and grew denser still. Over millions of years, those tiny density differences, imprinted during the inflationary epoch, grew into the large-scale structure of the universe. The galaxies, the galaxy clusters, the vast cosmic web of filaments and voids that fill space today, all of it traces back to quantum fluctuations in the inflaton field. Fluctuations that were stretched from subatomic scales to cosmic scales in less time than it takes to blink. This is not speculation. We can see the fingerprints of those fluctuations. The cosmic microwave background, the faint glow of radiation from when the universe was 380,000 years old, is not perfectly uniform. It has tiny temperature variations, hot spots and cold spots, that differ by about 1 part in 100,000. Those variations are the quantum fluctuations frozen into the fabric of space during inflation. Satellites like COBE in the early 1990s, the MAP in the 2000s, and Planck in the 2010s mapped those fluctuations in exquisite detail. And the pattern matches the predictions of inflation almost perfectly. The fluctuations are Gaussian, meaning their distribution follows a bell curve. They're scale invariant, meaning they look roughly the same at all sizes. And they're adiabatic, meaning the temperature variations correspond to density variations in a specific way. All of those properties are what inflation predicts. And all of them are what we observe. The match is so good that inflation has become the standard framework for understanding the early universe, despite the fact that we've never directly detected the inflaton field and probably never will. But the implications go further. Because if inflation happened, if space really did expand exponentially from a quantum fluctuation, then the observable universe, everything we can see with our most powerful telescopes, is just a tiny patch of a much larger inflated region. Imagine inflating a balloon. You draw a small dot on the balloon before you start, then you inflate it to the size of a planet. The dot is still there, but it's now stretched across a huge area. And the rest of the balloon, the parts that were originally far from the dot, are now so far away that light from them hasn't had time to reach the dot yet. That's the situation we're in. The observable universe, the roughly 93 billion light-year diameter sphere centered on Earth, is the dot. The rest of the inflated region is out there somewhere, beyond the cosmic horizon, causally disconnected from us. We can't see it, we can't reach it. But if inflation is right, it's there. And it's probably much, much larger than the part we can observe. How much larger? Nobody knows. The answer depends on how long inflation lasted and how fast space was expanding. Some models suggest the full inflated region is 10 to the 26 times larger than the observable universe. Others suggest it's infinite, literally infinite. An endless expanse of space filled with galaxies and stars and planets, stretching in all directions forever. Most of it will never be visible to us because the expansion of space carries distant regions away faster than light can travel. But it's out there, a consequence of the same process that smoothed out our local patch and seeded the galaxies we see in the night sky. The observable universe is not the universe. It's a small bubble inside a much larger structure. And that realization, more than anything else inflation predicts, changes how we think about our place in the cosmos. There's also a darker implication. If inflation can happen once, it can happen again. In fact, some versions of inflation theory suggest that it never really stops. The idea, called eternal inflation, is that once inflation starts in one region of space, quantum fluctuations can trigger new, inflationary regions elsewhere. Those regions inflate and produce their own patches of space, and within those patches more fluctuations trigger more inflation. The process becomes self-perpetuating, a runaway cascade where new universes are constantly budding off from older ones, each inflating, cooling, forming galaxies, and potentially spawning new inflationary regions of their own. In this picture, the Big Bang is not the beginning of everything. It's the beginning of our bubble, our local patch of space-time. But there are other bubbles, possibly infinite numbers of them. Each with its own history, its own physical laws, its own set of constants. The multiverse is not a fringe idea dreamed up by philosophers. It's a prediction that falls out of taking inflation seriously. And it's a prediction that makes a lot of physicists uncomfortable because if it's true, it means we can never test whether it's true. The other bubbles are beyond our cosmic horizon. We can't see them. We can't visit them. We can't measure their properties. All we can do is infer their existence from the mathematics of inflation and hope that someday someone figures out a clever way to detect their influence. But let's not get too far ahead. We're still trying to understand how inflation works and why it matters for the universe's origin. The core idea is simple. The universe started small. Some scalar field, the inflaton, was in a high-energy state. That state acted like vacuum energy, driving exponential expansion. Space inflated by an enormous factor in a fraction of a second. Quantum fluctuations in the inflaton field were stretched to cosmic scales, seeding the density variations that later became galaxies. Then the inflaton field transitioned to its low-energy state, dumping its energy into ordinary particles and radiation. Inflation ended. The universe continued expanding, but at a much slower rate. And from that point forward, the standard Big Bang model takes over. The universe cooled, protons and neutrons formed, atoms assembled, stars ignited, galaxies took shape, life appeared. All of it downstream of that brief inflationary burst. The genius of inflation is that it takes the fine-tuning problems that plague the standard Big Bang model and makes them disappear. You don't need to assume the universe started out flat. Inflation flattens it. You don't need to assume distant regions started with the same temperature. Inflation stretches them from a single small patch that had time to equilibrate. You don't need to worry about magnetic monopoles cluttering up the universe. Inflation dilutes them to undetectable levels. 3 major problems, all solved by one mechanism. And as a bonus, inflation also explains where the seeds of structure came from. The quantum fluctuations that got stretched to cosmic scales are not some ad hoc addition to the theory. They're a natural consequence of the inflaton field being quantum. You get them for free. And they match the observations. The cosmic microwave background, the distribution of galaxies, the large-scale structure of the universe, all of it fits the pattern inflation predicts. That's why inflation has become the dominant framework in cosmology. Not because it's proven beyond doubt. It's not. We don't have direct evidence of the inflaton field. We don't have a smoking gun observation that says, yes, this definitely happened. What we have is a mountain of indirect evidence: the smoothness of the microwave background, the flatness of space, the scale invariant distribution of fluctuations. All of it consistent with inflation, all of it hard to explain without inflation, and the more precisely we measure the universe, the better the match gets. The Planck satellite, which mapped the microwave background with unprecedented accuracy, found that the fluctuations matched the predictions of the simplest inflationary models to within a fraction of a percent. That's not proof, but it's close enough that most cosmologists are willing to bet the idea is right. Still, there are questions, big ones. What is the inflaton field? Where did it come from? Why was it in a high-energy state to begin with? Why did it transition to a low-energy state when it did, and not earlier or later? And what determines the specific parameters of inflation, the rate of expansion, the duration, the amplitude of the fluctuations? Different inflationary models give different answers. Some invoke a single inflaton field with a smooth potential. Others invoke multiple fields interacting in complicated ways. Some models predict that inflation lasts just long enough to solve the flatness and horizon problems. Others predict eternal inflation and a multiverse. The details matter because they determine what kind of universe you end up with. But the details are also where the theory gets speculative. We don't have direct observations of the inflaton. We can't measure its properties in a lab. All we can do is build models, make predictions, and compare those predictions to what we see in the sky. One of the most intriguing predictions of inflation is the existence of primordial gravitational waves. These are ripples in space-time itself, generated by the rapid expansion during inflation. They're different from the gravitational waves we've detected with LIGO and Virgo, which come from colliding black holes and neutron stars. Primordial gravitational waves would be a relic of the inflationary epoch, a direct fingerprint of the exponential expansion. And they would leave a distinctive imprint on the polarization of the cosmic microwave background, a pattern called B-mode polarization. Several experiments have tried to detect this signal. In 2014, a team working with the BICEP 2 telescope at the South Pole announced they'd found it. The physics community erupted with excitement. Here, finally, was direct evidence of inflation, the smoking gun. Except it wasn't. Follow-up observations revealed that the signal was contaminated by dust in our own galaxy. The B-modes were real, but they weren't primordial. They were foreground noise. The search continues. Several next-generation experiments are being built to hunt for primordial gravitational waves with better sensitivity and better foreground subtraction. If they find them, it will be the most direct confirmation of inflation we could ask for. If they don't, it will mean either inflation didn't happen the way we think it did, or the signal is too faint to detect with current technology. There's also the question of what inflation tells us about the origin of the universe. Because if the universe started as a quantum fluctuation in the foam, and inflation is what grew that fluctuation into the cosmos we observe, then inflation is not just a detail of early universe physics, it's the mechanism by which something emerged from the quantum substrate. The transition from timeless probabilistic foam to classical expanding spacetime. Without inflation, a quantum fluctuation might pop into existence and then collapse back into the foam before anything interesting happens. But with inflation, a fluctuation that happens to land in the right state, where the inflaton field is in its high-energy configuration, gets locked into a runaway expansion. The fluctuation doesn't collapse, it grows, and once it's large enough, once the inflaton field has dumped its energy into particles and radiation, the universe becomes stable, classical, real. Inflation is the engine that takes potential and turns it into actuality. That converts a probabilistic seed into a deterministic cosmos. This is why some physicists argue that inflation is more than just a solution to cosmological puzzles, it's a theory of cosmic origins, a description of how universes are born. And if eternal inflation is right, if the process is self-perpetuating, then the quantum foam is not just the substrate our universe emerged from, it's a factory. A mechanism that continuously generates new universes, each inflating from its own quantum fluctuation, each carrying its own set of physical laws and constants. The multiverse in this picture is not a static collection of parallel worlds. It's a dynamic, ever-growing structure, new branches budding off constantly, old branches expanding and cooling and forming galaxies, and all of it driven by the same inflationary mechanism that created our own observable universe 13.8 billion years ago. That's heady stuff. It's also frustrating because it pushes the ultimate origin question back a step without really answering it. Okay, fine. Inflation explains how our universe grew from a quantum fluctuation. But where did the quantum foam come from? Why does it have the properties it does? Why does it produce inflaton fields capable of driving exponential expansion? And why do those fields sometimes start in high-energy states that trigger inflation? These are the questions inflation doesn't answer. It takes the fine-tuning problem of the Big Bang and replaces it with a different set of fine-tuning problems at a deeper level. You've traded the mystery of why the universe started flat and smooth for the mystery of why the quantum foam produces inflaton fields and why those fields behave the way they do. It's progress. Real progress. But it's not the end of the story. Still, let's not lose sight of what inflation accomplishes. It explains the smoothness of the universe. It explains the flatness. It explains the absence of monopoles. It explains the origin of structure, the seeds of galaxies, from quantum fluctuations. It predicts a pattern of fluctuations in the microwave background that matches observations to extraordinary precision. It tells us that the observable universe is a tiny patch of a much larger inflated region. And it provides a plausible mechanism for how a quantum fluctuation could grow into a macroscopic cosmos. That's not nothing. That's a framework that unifies multiple independent observations under a single coherent theory. And it does so without requiring egregious fine-tuning or invoking mysterious external causes. Inflation is strange. It's counterintuitive. It requires accepting that space can expand faster than light, and that quantum fluctuations can be stretched to cosmic scales. But it works. The predictions match the data. And until someone comes up with a better explanation, inflation is the best answer we have for how the universe transitioned from a subatomic seed to the vast structure we observe today. So where does that leave us? Standing at the end of the inflationary epoch, roughly 10 to the negative 34 seconds after the Big Bang, looking out at a universe that has just finished its exponential growth spurt. Space is smooth, flat, filled with the energy released when the inflaton field transitioned to its low-energy state. That energy is about to convert into particles. Quarks, electrons, photons, all the fundamental constituents of matter and radiation. The universe is hot, unimaginably hot. But it's cooling as it expands, and as it cools, it's going to pass through a series of phase transitions, moments where the rules change and new structures become possible. Quarks will bind together into protons and neutrons. Protons and neutrons will fuse into light atomic nuclei. Electrons will eventually combine with nuclei to form neutral atoms, releasing the photons that will become the cosmic microwave background. And from those atoms, over millions of years, stars will ignite, galaxies will assemble, and the universe will take on the form we recognize today. All of that is downstream of inflation. The seeds were planted during that brief exponential burst. Now it's time to watch them grow, to see how the quantum fluctuations stretched to cosmic scales during inflation turned into the galaxies and clusters and filaments that fill the night sky. How the universe transitioned from a smooth, featureless plasma to the richly structured cosmos we inhabit. That transition, from simplicity to complexity, from uniformity to diversity, is where the real story begins. Because inflation sets the stage, but it doesn't write the script. What happens next, how matter clumps together, how gravity shapes the large-scale structure, how the first stars ignite and the first galaxies form, that's the next chapter. The story of how the universe went from a hot, dense soup of particles to the cosmic egg that eventually hatched everything we see. We left off watching the universe finish its exponential growth spurt, roughly 10 to the negative 34 seconds after the Big Bang, staring at a cosmos that had just inflated from smaller than a proton to larger than a galaxy in less time than it takes light to cross an atomic nucleus. Space is smooth now, flat, stretched by that runaway expansion into a state so uniform that distant regions look nearly identical, despite never having been in contact. The inflaton field, the mysterious scalar field that drove inflation, is still there, still dominating the energy density of the universe, but it's about to do something crucial. It's about to decay. And when it does, when that field transitions from its high energy state to its low energy state, the energy that was driving inflation has to go somewhere. It doesn't just vanish. Energy is conserved, even in the early universe, So the inflaton dumps its energy into the only place it can, into particles, ordinary standard model particles. Quarks, electrons, photons, neutrinos, all the fundamental constituents of matter and radiation. This process is called reheating, and it's the moment the universe transitions from the bizarre inflationary regime into something closer to the standard Big Bang model we've been describing for decades. Without reheating, inflation would leave the universe catastrophically empty. A vast, smooth, flat expanse of space with almost nothing in it. Reheating is what repopulates the cosmos, what turns the inflaton's vacuum energy into the hot, dense soup of particles that will eventually cool, clump, and form everything we see today. The name reheating is a little misleading because it suggests the universe was hot before, cooled down during inflation, and then heated back up. That's not quite what happens. During inflation, the universe was expanding so fast that any ordinary matter or radiation present at the start got diluted to near zero. The temperature, in the usual thermodynamic sense, dropped precipitously, but the inflaton field itself was carrying an enormous amount of energy. When that field decays, when it oscillates and fragments and converts its energy into particles, those particles are created with enormous kinetic energies. They're moving fast, colliding, interacting. And that collective motion, that kinetic energy distributed across a vast number of particles, is what we measure as temperature. So the universe heats up again. Not because energy is being added from outside, but because the energy that was locked up in the inflaton field is now expressed as the thermal motion of particles. Reheating is less like turning a stove back on, and more like watching a tightly wound spring suddenly release, converting potential energy into kinetic energy in a burst. The details of how reheating happens depend on the specific properties of the inflaton field, which we don't know because we've never directly observed the inflaton. Different models predict different reheating mechanisms. In some, the inflaton decays directly into standard model particles through interactions built into the field's equations. In others, the inflaton first decays into intermediate particles that then decay into the particles we know. The timescales vary depending on how strongly the inflaton couples to other fields. Some models suggest reheating happens almost instantaneously after inflation ends. Others suggest it takes a bit longer, with the inflaton oscillating back and forth in its potential well before finally decaying. But the end result is the same. By the time reheating is done, the universe is filled with a hot, dense plasma of particles. The temperature estimates vary depending on the model, but typical values place the reheating temperature somewhere between 10 to the 9th and 10 to the 15th Kelvin. That's 1 billion to a quadrillion degrees. Hot enough that no structures can form. Hot enough that even protons and neutrons, the particles that will eventually make up atomic nuclei, can't hold themselves together yet. At these temperatures, matter as we understand it does not exist. What exists instead is a roiling sea of quarks, gluons, leptons and photons, all interacting furiously, colliding, annihilating, reforming, in a state of near-perfect thermal equilibrium. This is the quark-gluon plasma. A state of matter so extreme, so alien to everyday experience, that we've only managed to recreate it briefly in particle colliders by smashing heavy ions together at near-light speed. The universe spent its first few microseconds in this state. Not minutes, not seconds, microseconds. 1/millionth of a second. That's how fast things were happening. The universe was expanding, cooling, transitioning through regimes of physics, at a pace that makes the entire history of human civilization look glacial by comparison. At these temperatures, quarks, the fundamental building blocks of protons and neutrons, are not confined inside particles. They're free, swimming through the plasma, interacting with gluons, the particles that carry the strong nuclear force. In normal conditions, quarks are never found alone. The strong force binds them together so tightly that trying to pull a quark out of a proton is like trying to stretch a rubber band to infinity. The harder you pull, the more energy you pump into the system, until eventually you've added enough energy to create a new quark-antiquark pair and you're back where you started. This is called confinement, and it's one of the defining features of the strong force. But at high enough temperatures, confinement breaks down. The thermal energy is so intense that quarks can move freely over distances much larger than the size of a proton. The plasma becomes a kind of quark soup, with individual quarks and gluons zipping around, colliding, exchanging energy, in a state that looks more like a liquid than a gas. That last part is surprising. For a long time, physicists assumed the quark gluon plasma would behave like an ideal gas, with particles moving independently, colliding occasionally, but mostly doing their own thing. Experiments at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, and later at the Large Hadron Collider's Heavy Ion program, revealed something different. The plasma behaves like a nearly perfect fluid. It has almost no viscosity. When you disturb it, the disturbance propagates smoothly, without the kind of dissipation you'd expect from a gas. The quarks and gluons are interacting so strongly, exchanging momentum so efficiently, that they move collectively rather than independently. It's one of the most strongly coupled systems ever observed, which is strange because the strong force, despite its name, becomes weaker at high energies, a phenomenon called asymptotic freedom. At the temperatures of the quark-gluon plasma, you'd expect the quarks to interact weakly, to behave almost like free particles. But the plasma doesn't care what you expect. It does what the equations say, and the equations say the interactions are strong enough to produce collective behavior. The early universe, for a few microseconds, was filled with a nearly frictionless liquid of quarks and gluons, hotter than the core of any star, denser than a neutron star, expanding and cooling so fast that the state didn't last long enough for any structure to form. As the universe expanded, the temperature dropped, not linearly. The temperature falls inversely with the size of the universe. Double the size, halve the temperature. And because the universe was expanding exponentially during inflation, and then much more slowly during the radiation-dominated era that followed reheating, the temperature curve looks like a cliff. During inflation, if you could even define temperature in that regime, it plummets. After reheating, it starts high and drops steadily but much more gradually. By the time the universe was about 10 microseconds old, the temperature had fallen to roughly 1 trillion Kelvin. Still absurdly hot by any human standard, but cool enough for something important to happen. The quarks, which had been freely roaming the plasma, started to bind together. The strong force, which had been temporarily overwhelmed by the thermal energy, reasserted itself. Quarks combined into hadrons, particles made of bound quarks, protons, which are made of 2 up quarks and 1 down quark, neutrons, which are 2 down quarks and 1 up quark, and a whole zoo of other less stable particles that quickly decayed into protons, neutrons, and lighter particles like pions and kaons. This transition, from a plasma of free quarks and gluons to a gas of bound hadrons, is called the quark-hadron transition, and it marks the end of the quark-gluon plasma era. After this point, quarks are confined inside particles. They will never again be free in the way they were during those first microseconds. The universe has cooled enough that the structure of matter, the building blocks that will eventually form atoms and molecules and everything solid you've ever touched, has started to take shape. But we're not done yet. Because protons and neutrons, as stable as they seem in the modern universe, are not stable at these temperatures. At 1 trillion Kelvin, particles are still moving so fast, colliding so violently, that even bound hadrons can be smashed apart. The universe is in a constant state of flux. Protons colliding with antiprotons and annihilating into photons. Photons colliding and creating proton-antiproton pairs. Neutrons decaying into protons. Protons capturing electrons and turning into neutrons. The whole system is in thermal equilibrium, with particles constantly converting back and forth between different forms at a rate determined by the temperature. As the universe continues to expand and cool, the balance starts to shift. The photons lose energy. They're no longer energetic enough to create new proton-antiproton pairs. But the protons and antiprotons that already exist can still find each other and annihilate, and they do. The vast majority of the matter and antimatter in the early universe wipes itself out, converting back into radiation. What's left? The tiny surplus of matter over antimatter, about 1 extra proton for every billion proton-antiproton pairs, is everything we see today. Every star, every planet, every atom in your body, all of it came from that tiny asymmetry. If matter and antimatter had been perfectly balanced, the universe would be empty except for photons. No structure, no chemistry, no life. The fact that we exist means there was a slight imbalance baked into the early universe and nobody knows why. Explaining that asymmetry, that slight excess of matter over antimatter, is one of the major unsolved problems in cosmology. We know it happened, we can measure the effects, but we don't know the mechanism. The standard model of particle physics doesn't predict it. There are extensions, ideas involving new physics at high energies that could explain it, but we don't have direct evidence for any of them yet. By the time the universe is about 1 second old, the temperature has dropped to about 10 billion Kelvin. Still hot enough to melt any known material instantly, but cool enough that neutrinos, the ghostly, nearly massless particles that interact so weakly with matter they can pass through light years of lead without flinching, stop interacting with the rest of the plasma. Up until this point, neutrinos were in thermal equilibrium with everything else. They were scattering off electrons and positrons, exchanging energy, maintaining the same temperature as the surrounding plasma. But as the density drops and the temperature falls, the rate of neutrino interactions plummets, the neutrinos decouple, they stop colliding with anything. From this point forward, they stream freely through the universe, a relic background of low-energy particles that fill all of space but almost never interact with anything. We call this the cosmic neutrino background, and it's one of the predicted relics of the Big Bang that we've never directly detected. The neutrinos are out there, roughly 330 per cubic centimetre in the modern universe, moving at close to the speed of light, passing through your body at a rate of about 100 trillion per second without leaving a trace. Detecting them directly is nearly impossible because they interact so weakly. But their existence is baked into the cosmological models, and those models match the observations so well that most physicists are confident the neutrino background is real even if we can't see it. Around the same time, another transition happens. The universe cools enough that electrons and positrons, which had been in thermal equilibrium with photons, start annihilating without being replaced. Just like the protons and antiprotons earlier, the electrons and positrons find each other and convert back into radiation. Most of them disappear. What's left is a small surplus of electrons, exactly matching the surplus of protons because the universe has to stay electrically neutral. Those leftover electrons will eventually pair up with protons to form hydrogen atoms, but not yet. The universe is still too hot. If an electron and a proton try to bind together into an atom, a passing photon will smash them apart almost immediately. The plasma is still ionized, meaning the electrons are not bound to nuclei. They're free to roam, scattering photons, keeping the universe opaque. Light can't travel far because every photon keeps hitting an electron and bouncing off in a random direction. The universe, despite being filled with light, is not transparent. It's a glowing fog. That will change, but not for another few 100,000 years. The next major milestone happens a few minutes after the Big Bang. This is Big Bang nucleosynthesis, the period when the first atomic nuclei form. Up until now, the universe has been too hot for nuclei to survive. Protons and neutrons existed, sure, but if they tried to stick together, the thermal collisions would knock them apart. But as the temperature continues to drop, passing below about 1 billion Kelvin, the conditions become just right. Protons and neutrons can bind together into light nuclei without being immediately destroyed. The process starts simple. A proton and a neutron combine to form deuterium, heavy hydrogen, a nucleus with 1 proton and 1 neutron. Deuterium is fragile. In the modern universe, it's rare because it gets burned up in stars, but in the early universe, it's the first step in building heavier elements. Once you have deuterium, you can add another neutron to make tritium, or another proton to make helium-3. And if 2 deuterium nuclei collide, they can fuse into helium-4, the most stable light nucleus, with 2 protons and 2 neutrons. This is the same reaction that powers hydrogen bombs in the core of the Sun. In the early universe, it happened everywhere, all at once, in a brief burst of fusion that lasted about 3 minutes. 3 minutes. That's the entire window for Big Bang nucleosynthesis. Before that, the universe was too hot. After that, it had cooled and expanded enough that the density dropped below the threshold needed for fusion. The protons and neutrons were too far apart to find each other and react, so everything that was going to fuse, fused in that narrow window. And what came out the other side was a universe made almost entirely of hydrogen and helium. About 75% hydrogen, meaning lone protons that never found a neutron to bind with. About 25% helium-4, meaning nuclei with 2 protons and 2 neutrons, and tiny trace amounts of deuterium, helium-3, and lithium-7. Everything else, every element heavier than lithium, was not made in the Big Bang. Carbon, oxygen, iron, gold, all of it came later, forged in the cores of stars and scattered across space when those stars exploded. But the hydrogen and helium the raw material that makes up the bulk of the universe's visible matter that came from nucleosynthesis, and the ratios, the 75-25 split, are one of the major predictions of Big Bang cosmology. You can calculate what those ratios should be based on the temperature, density, and expansion rate of the early universe, and then you can go out and measure the actual abundances of hydrogen and helium in old stars and gas clouds, places where the material hasn't been significantly processed by stars, and the numbers match, almost perfectly. The universe contains exactly the amount of helium the Big Bang model predicts. That match is one of the strongest pieces of evidence we have that the hot Big Bang really happened. There's a subtlety here worth noting. The ratio of neutrons to protons at the time of nucleosynthesis determines how much helium gets made. Neutrons are slightly heavier than protons, which means in thermal equilibrium there are fewer neutrons than protons. As the universe cooled, the neutron-to-proton ratio was about 1:6. But neutrons are unstable. A free neutron will decay into a proton, an electron, and an antineutrino with a half-life of about 10 minutes. So during the few minutes between when the temperature dropped low enough for nucleosynthesis to start, and when the density dropped low enough for it to stop, some of the neutrons decayed. By the time nucleosynthesis actually got going, the ratio had shifted to about 1 neutron for every 7 protons. Almost all of those neutrons ended up in helium-4 nuclei because helium-4 is so stable. 2 protons, 2 neutrons, bound together in a nice tight package. That means for every 2 neutrons you get 1 helium nucleus, and because there was 1 neutron for every 7 protons, you end up with about 1 helium nucleus for every 12 protons. Do the mass ratios and you get roughly 25% helium by mass. The numbers work out beautifully, and the fact that they do is not an accident. It's a consequence of the physics operating in the early universe, the weak interaction determining the neutron decay rate, the strong interaction determining the binding energies of nuclei, the expansion rate setting the timescale for reactions. All of it fits together in a way that would be nearly impossible to fake. Big Bang nucleosynthesis also provides a constraint on the number of neutrino species. This sounds like an odd detail, but it's important. The expansion rate of the universe during nucleosynthesis depends on the total energy density, and every type of particle that exists contributes to that density. More particle types means higher density means faster expansion. Faster expansion means less time for nucleosynthesis, which changes the final abundances of deuterium and helium. By measuring those abundances and comparing them to theoretical predictions, cosmologists can infer how many types of light, weakly interacting particles were present during nucleosynthesis. The answer comes out to about 3 neutrino families, which matches exactly what particle physics experiments have found: the electron neutrino, the muon neutrino, and the tau neutrino. If there were a 4th type of neutrino or any other light weakly interacting particle, it would have left a fingerprint in the abundances of light elements. The fact that we don't see that fingerprint tells us the Standard Model's particle content is complete, at least as far as light particles go. That's a powerful constraint. It's cosmology and particle physics talking to each other and agreeing. After nucleosynthesis, the universe continues expanding and cooling. For the next several 100,000 years, not much happens. The plasma is still ionized, electrons are still free, photons are still scattering constantly, keeping the universe opaque. The temperature drops, but slowly. The universe is in what's called the radiation-dominated era, where the energy density is mostly in the form of photons and other relativistic particles moving at or near the speed of light. Matter exists, sure, but it's a minority component. The universe is a fog of light with some hydrogen and helium nuclei drifting through it. Then, about 380,000 years after the Big Bang, the temperature finally drops below about 3000 Kelvin. That's cool enough, barely, for electrons and protons to combine into neutral hydrogen atoms without being immediately ionized by passing photons. This process is called recombination, though the name is misleading because the electrons and protons are combining for the first time, not recombining. But the name stuck. As recombination proceeds, the free electron density drops. Photons, which had been scattering constantly off those free electrons, suddenly have nothing to scatter off of. The universe becomes transparent. Light can travel freely across space without being absorbed or deflected. The photons that were trapped in the plasma, bouncing from electron to electron in an endless random walk, are suddenly released. They stream outward in straight lines, carrying with them a snapshot of the universe at that moment. Those photons are still travelling today. We detect them as the cosmic microwave background, the faint glow of radiation that fills the sky in every direction, with a temperature of about 2.7 Kelvin. The cosmic microwave background is one of the most important observations in all of cosmology. It's the oldest light we can see, a direct window into the state of the universe when it was less than 400,000 years old. Everything that happened before that moment is hidden behind the wall of the opaque plasma. We can't see further back directly because the universe was opaque, but we can see this moment with extraordinary clarity. Satellites like the Cosmic Background Explorer in the early 90s, the Wilkinson Microwave Anisotropy Probe in the 2000s, and the Planck satellite in the 2010s have mapped the microwave background with incredible precision. And what they found is a nearly perfect blackbody spectrum, the kind of radiation emitted by a perfect thermal emitter in equilibrium, with tiny fluctuations overlaid. Those fluctuations, temperature differences of about 1 part in 100,000, are the seeds of structure. Regions that were slightly denser at the time of recombination show up as slightly hotter spots in the microwave background. Regions that were slightly less dense show up as cooler spots. And those density differences, imprinted during inflation and preserved through the radiation-dominated era, are what eventually grew into galaxies. The pattern of fluctuations is not random. It has structure. Peaks and valleys at specific angular scales corresponding to sound waves that were propagating through the plasma before recombination. Yes, sound waves. Before the universe became transparent, the plasma was a fluid. Pressure waves could travel through it, compressing and rarefying the matter in oscillating patterns. Those waves were driven by the competition between gravity, which tried to pull matter together, and radiation pressure, which pushed it apart. The result was a series of oscillations, acoustic peaks, at specific scales determined by how far sound could travel in the time before recombination. When the universe became transparent, those oscillations were frozen into the distribution of matter, and we see them today as peaks in the power spectrum of the cosmic microwave background. The location, height, and spacing of those peaks encode enormous amounts of information about the universe's composition, geometry, and history. By measuring them, cosmologists have been able to pin down the age of the universe, the density of matter, the density of dark energy, the rate of expansion, and the amplitude of the initial fluctuations to within a few percent. The cosmic microwave background is not just a baby picture of the universe, it's a forensic report. There's something deeply strange about the cosmic microwave background that's worth pausing on. The photons we detect today have been travelling for more than 13 billion years. They left the surface of last scattering, the moment when the universe became transparent, and headed out in straight lines. Some of them ended up here, hitting our detectors, telling us what the universe looked like back then. But here's the thing, those photons were not aimed at us. They were not emitted in our direction. They were emitted in every direction, equally from every point in the plasma. The reason we see them is that the universe has expanded so much that the region we now call the surface of last scattering is now 46 billion light-years away in every direction, even though the photons have only been travelling for 13.8 billion years. The expansion of space carried the source of the photons away from us faster than the photons could travel toward us. We're seeing light from a place that's now unreachably distant, from a time when that place was close enough for light to reach us. The cosmic microwave background is a kind of spherical shell surrounding us, centered on Earth not because we're special, but because we're the observers. Every observer in the universe sees their own cosmic microwave background, a sphere of ancient light centered on wherever they happen to be. It's a consequence of the finite speed of light combined with the expansion of space, and it means the observable universe has an edge not in space but in time. We can't see past the surface of last scattering because the universe was opaque before that. The microwave background is the cosmic horizon, the furthest back we can look with electromagnetic radiation. After recombination, the universe entered what's called the Dark Ages, not dark in the sense of having no light. The cosmic microwave background was still there, glowing brightly, but dark in the sense that there were no stars yet, no galaxies. Just a vast, cooling, expanding cloud of neutral hydrogen and helium, slowly clumping together under the pull of gravity. This period lasted for a few 100 million years, maybe longer. The density fluctuations imprinted during inflation were still there, still growing. Slightly denser regions attracted more matter. As they grew denser, their gravitational pull strengthened. They attracted even more matter. The process is called gravitational instability, and it's self-reinforcing. Small fluctuations grow into larger fluctuations. Larger fluctuations grow into clumps. Clumps grow into filaments and halos, and eventually, in the densest regions, the gas collapses far enough and heats up enough that nuclear fusion ignites. Stars are born. The first stars, the population 3 stars we've never observed directly, were likely enormous. Hundreds of times the mass of the Sun, made purely of hydrogen and helium because there were no heavier elements yet. They burned hot and fast, living only a few million years before exploding in supernovae that seeded the surrounding gas with the first heavy elements. Those explosions enriched the interstellar medium, allowing the next generation of stars to form with a more diverse chemistry. And from those stars, galaxies began to assemble. The timeline here is still being refined. For a long time, the assumption was that the first stars formed around 200 million years after the Big Bang. Then the James Webb Space Telescope started finding galaxies at redshifts so high they correspond to the universe being only a few 100 million years old. Some of those galaxies are surprisingly massive and well-formed, which suggests the first stars might have ignited earlier than anyone expected. The details are still being worked out, but the broad picture is clear. The universe went from a smooth, uniform plasma to a richly structured cosmos filled with galaxies, clusters, and voids over the course of a few 100 million years. And all of that structure traces back to the quantum fluctuations imprinted during inflation, the same fluctuations we see as tiny temperature differences in the cosmic microwave background. The seeds of structure were planted in the first fraction of a second. They spent hundreds of thousands of years frozen in the plasma. Then, after recombination, they started to grow. Gravity took over. Matter clumped together. Stars ignited. Galaxies formed. And the universe transitioned from a featureless expanse into the complex, dynamic, beautiful mess we see today. There's a precision to all of this that's easy to overlook. The universe didn't just randomly stumble into forming stars and galaxies. The conditions had to be just right. If the initial fluctuations were a little smaller, gravity wouldn't have been strong enough to pull matter together. The universe would have remained smooth with no structure, no stars, no planets, no us. If the fluctuations were a little larger, matter would have clumped together too quickly, forming black holes instead of stars, and again, no structure capable of supporting life. The amplitude of the fluctuations, measured at about 1 part in 100,000, sits in a narrow sweet spot. Not too strong, not too weak, just right. Similarly, the expansion rate of the universe, the balance between matter and radiation, the timing of nucleosynthesis and recombination, all of it had to line up in a very specific way for the universe to look the way it does. Change any of those parameters by more than a few percent and you get a universe that looks radically different. Maybe one that's still expanding too fast for galaxies to form. Maybe one that collapsed back on itself before stars could ignite. Maybe one where nucleosynthesis produced too much helium and not enough hydrogen, so stars couldn't form the way they do in our universe. The cosmic egg, the hot, dense state that emerged from the end of inflation, was not a generic blob of energy. It was a carefully tuned system, poised on a knife edge, with properties that allowed complexity to emerge. That tuning bothers a lot of physicists. It feels too convenient. Why should the universe have started with conditions so finely balanced that stars and galaxies and eventually life became possible? One answer is the anthropic principle. We observe a universe capable of producing observers because if it weren't, we wouldn't be here to notice. It's a selection effect. The universe looks fine-tuned because we're only able to ask the question in a universe that's fine-tuned. In a lifeless universe, there's nobody around to wonder why things look the way they do. That argument is logically sound but deeply unsatisfying because it replaces a mechanistic explanation with a statistical one. Another answer is the multiverse, which we'll get into soon. If there are countless universes, each with different properties, then some of them will happen to have the right conditions for structure and life, and we happen to live in one of those. Again, logically sound, but frustrating because it pushes the explanation beyond what we can ever hope to test. A third answer is that maybe the parameters aren't as finely tuned as they seem. Maybe there's some deeper principle, some symmetry or constraint we haven't discovered yet, that forces the universe to have these properties. That would be the most satisfying answer because it would give us a mechanism, a reason. But we don't have that reason yet. All we have is the observation that the universe started with a set of initial conditions that, for reasons we don't fully understand, were exactly what they needed to be for everything that followed. The forces themselves, the four fundamental interactions that govern the behaviour of matter and energy, also settled into their current forms during this period. During the Planck epoch, they were unified, or at least much closer to being unified than they are now. As the universe cooled and expanded, the forces split apart one by one. Gravity separated first at the end of the Planck epoch. The strong force separated from the electroweak force at the grand unification scale, around 10 to the negative 36 seconds. The electromagnetic and weak forces remained merged until the electroweak phase transition, around 10 to the negative 12 seconds, when the Higgs field acquired its non-zero value and gave particles their masses. From that point forward, the four forces operated independently, each with its own strength, range and set of rules. And those rules, the specific values of the coupling constants that determine how strongly each force interacts, are another part of the fine-tuning puzzle. Change the strength of the electromagnetic force by a few %, and atoms either fly apart or collapse. Change the strength of the strong force and nuclei can't hold together. Change the strength of gravity and stars either burn out too quickly or never ignite at all. The forces, like the initial conditions, sit in a narrow range that permits complexity. Why? Nobody knows. So where are we now? We've traced the universe from the end of inflation, through reheating, through the quark-gluon plasma era, through nucleosynthesis, through recombination and the release of the cosmic microwave background, all the way to the formation of the first stars and galaxies. From a smooth, hot, dense state to a richly structured cosmos in less than 1 billion years. From a universe smaller than an atom to one spanning billions of light years. From pure energy to matter and radiation in a careful balance. From quantum foam and inflaton fields to hydrogen atoms and starlight, the cosmic egg hatched. And what emerged was not chaos. It was order, structure, a universe that started simple and became complex, that started uniform and became diverse. A universe that, for reasons we're still trying to understand, was capable of producing galaxies, stars, planets, and eventually life. The story so far is the story of how the universe went from nothing, or something very close to nothing, to everything. How the quantum fluctuations of the inflaton field grew into galaxies. How the decay of the inflaton filled space with particles. How those particles cooled and combined into nuclei and atoms. How gravity pulled those atoms together into stars. And how those stars, burning and exploding over billions of years, forged the heavy elements that make up planets and people. That's the narrative arc of cosmology, the universe's origin story. And it's a story we've been able to reconstruct in extraordinary detail by combining observations of the microwave background, the abundances of light elements, the distribution of galaxies, and the theoretical framework of general relativity, quantum mechanics, and particle physics. But there's a question lurking underneath all of this, a question we've been dancing around but not confronting directly. If the universe emerged from a quantum fluctuation in the foam, and if inflation is a generic process that happens whenever the inflaton field lands in the right state, then why should we assume it only happened once? If the quantum foam is timeless and constantly fluctuating, producing seeds that occasionally inflate into universes, then maybe our universe is not unique. Maybe it's one bubble among countless others, each with its own history, its own set of physical laws, its own values for the fundamental constants. Maybe the fine-tuning we've been worrying about is not a cosmic coincidence or a deep principle waiting to be discovered, but a simple selection effect. We live in a universe with these parameters because universes with these parameters are capable of producing observers. Other universes exist with different parameters, but nobody's there to notice. The multiverse is not a fringe idea anymore. It's a prediction that falls out of taking eternal inflation seriously. And while we can't see those other universes, can't visit them, can't test whether they exist, the mathematics suggest they should. That our observable universe is a single finite bubble in an infinite ever-growing structure. A single chapter in a story that has no beginning and no end. And that possibility, that our universe might be one among infinite others, is where we're going next. We left off watching the first stars ignite, galaxies assembling from the seeds of quantum fluctuations stretched to cosmic scales during inflation, the universe transitioning from a smooth featureless plasma to the richly structured cosmos we see today. Everything traced back to that brief inflationary burst, that fraction of a second when space expanded exponentially and set the stage for everything that followed. The cosmic egg hatched, and what emerged was our universe. Galaxies, stars, planets, the whole magnificent structure stretching billions of light years in every direction. And for a long time, that was enough. One universe, one Big Bang, one origin story. The question of what came before was strange enough. The question of what came alongside never even occurred to most people. But once you start taking inflation seriously, once you follow the mathematics to its logical conclusion, a deeply uncomfortable possibility emerges. What if our universe is not unique? What if the same mechanism that created our bubble of space-time is constantly creating others? What if the Big Bang was not the beginning of everything, but just the beginning of our local patch, one spark in an infinite cascade? What if right now, beyond the cosmic horizon, there are other universes being born, expanding, forming their own galaxies, operating under their own rules? This is not science fiction. This is where the equations lead if you take them seriously, and it changes everything. The idea of multiple universes is old. Philosophers have been kicking it around for centuries. The ancient Greeks speculated about infinite worlds. Medieval scholars debated whether God could have created more than one cosmos. Science fiction writers have been mining the concept for plot twists since before quantum mechanics was even a thing. But the modern scientific multiverse is different. It's not a thought experiment or a narrative device. It's a prediction that falls out of our best theories of cosmology and particle physics. Nobody set out to invent the multiverse. It emerged, unwanted and unavoidable, from the mathematics of inflation and string theory. And once it showed up, physicists couldn't make it go away. The term multiverse itself is slippery because it describes not one idea, but a family of related ideas, each with different motivations and different levels of speculative distance from established physics. In 2003, a cosmologist named Max Tegmark published a paper that tried to bring some order to the chaos. He proposed a taxonomy, a classification scheme that divides multiverse ideas into 4 levels. Level 1, Level 2, Level 3, Level 4. Each more radical than the last, each harder to test, and each, in its own way, challenging the idea that our universe is the whole story. Level 1 is the simplest and also the least controversial. It's the idea that if space is infinite, which many cosmological models suggest it is, then the observable universe is not the universe. It's just the region we can see, the sphere of space from which light has had time to reach us since the Big Bang. Beyond that cosmic horizon, space keeps going. Forever. And if space is infinite and matter is distributed roughly uniformly, which observations suggest it is at very large scales, then every possible configuration of particles that can exist will exist somewhere. Not just once, infinitely many times, because in an infinite volume with finite possibilities, repetition is not just likely, it's guaranteed. This is not mysticism, this is combinatorics. There are only so many ways to arrange a finite number of particles in a finite volume. The number is absurdly large, something like 10 to the power of 10 to the power of 122, for a region the size of the observable universe, but it's finite. And if space goes on forever, with matter filling it in a similar way everywhere, then every one of those configurations must repeat. That includes the configuration you're sitting in right now, the arrangement of atoms in your body, the structure of your brain, the exact sequence of thoughts you're having at this moment. Somewhere out there, far beyond the cosmic horizon, there is a region of space identical to this one, an exact duplicate of you, sitting in an exact duplicate of your chair, reading an exact duplicate of this sentence. Not a copy in the sense of a simulation or a reflection, a physical duplicate made of real atoms in real space, existing right now, causally disconnected from you by the sheer distance and the expansion of space. Tegmark did the math. The distance to the nearest such duplicate, assuming the observable universe's matter density and using standard statistical arguments, is about 10 to the power of 10 to the power of 29 meters. That's a 1 followed by 10 billion trillion zeros. A number so large that writing it out would take more space than exists in the observable universe. For practical purposes, that duplicate might as well not exist. You will never meet them. No signal will ever pass between you. The expansion of space is carrying them away faster than light can travel. But mathematically, if space is truly infinite, and matter is distributed the way it appears to be, the duplicate is there. And not just one, infinitely many. Because in an infinite universe, anything that can happen will happen. Not just once, an infinite number of times. This bothers people, it should. The idea that there are infinite copies of you scattered across an infinite cosmos, living identical lives, making identical choices, reading identical sentences is profoundly strange. But level 1 multiverse logic does not require any new physics. It's just a consequence of taking standard inflationary cosmology seriously and combining it with the possibility that space is infinite. If those two things are true, if inflation made space flat and flat space can be infinite, then level 1 follows. No speculative particle physics, no exotic dimensions, just vanilla cosmology pushed to its logical conclusion. Most cosmologists treat level 1 as philosophically interesting but not particularly urgent because those distant regions are forever beyond our reach. They exist in the same space-time as we do, governed by the same laws, filled with the same types of particles. The only thing that's different is the initial conditions, different arrangements of matter, different histories, same rules. Level 2 is where things get strange. This is the multiverse that emerges from eternal inflation. We talked about inflation already, the brief period of exponential expansion that smoothed out the universe and seeded the fluctuations that became galaxies. But here's the catch. Inflation, once it starts, does not have to stop everywhere at once. In fact, in most inflationary models, it cannot stop everywhere at once. The inflaton field, the scalar field driving inflation, is quantum. It fluctuates. In some regions, the field decays from its high energy state to its low energy state, and inflation ends. Those regions transition into a more sedate expansion, cooling down, forming particles, eventually producing galaxies. That's what happened in our universe. But in other regions, quantum fluctuations push the inflaton field back up into its high energy state. Those regions keep inflating, and because inflation is exponential, because space doubles again and again, the regions that are still inflating grow much faster than the regions that stopped. The result is a never-ending cascade. A fractal structure where pockets of space stop inflating and become bubble universes, while the space between those bubbles continues inflating, producing more bubbles, which themselves continue inflating and producing more bubbles. Forever. This is eternal inflation, and it turns the Big Bang into a local event. Think of it like boiling water. When water reaches its boiling point, bubbles form. Each bubble is a region where the liquid has transitioned to vapor. The bubbles grow, rise, and eventually pop or merge. But as long as you keep heating the pot, new bubbles keep forming. The boiling never stops. Eternal inflation is similar, except the pot is the quantum foam, the water is the inflaton field in its high energy state, and the bubbles are universes. Each bubble is a region where the inflaton decayed, where inflation stopped, where space cooled down and structure formed. And each bubble is causally disconnected from the others because the space between them is expanding faster than light can travel. From the inside of a bubble, the other bubbles are not just far away. They're beyond the horizon, unreachable in principle. Each bubble is its own universe, with its own Big Bang, its own timeline, its own history. But here's where level 2 gets truly radical. The bubbles do not have to be identical. In fact, they probably are not. Because the properties of a universe, things like the masses of particles, the strengths of forces, even the number of dimensions of space might not be fixed. They might depend on the state of various quantum fields at the moment inflation ends in a given region. If different bubbles end up with different field configurations, they end up with different physical laws. Not just different initial conditions like level 1, different rules, a bubble where the electromagnetic force is stronger than it is here. A bubble where there are 4 large spatial dimensions instead of 3. A bubble where protons are heavier than neutrons and stable matter cannot form. Every variation that the underlying theory allows could be realized somewhere in the multiverse, and because eternal inflation keeps producing bubbles forever, every possibility gets explored. Not just once, infinitely many times. This is where string theory enters the picture. String theory, for all the hype and controversy surrounding it, is at its core an attempt to unify quantum mechanics and general relativity, to describe all particles and forces as vibrations of tiny strings, one-dimensional objects oscillating in 10 or 11 dimensions of space-time. Most of those dimensions are curled up so small we never notice them, but the specific way they're curled up determines what kinds of particles and forces appear in the 4 dimensions we experience. The geometry of the extra dimensions is called the compactification, and it turns out there are an enormous number of ways to compactify the extra dimensions. Not dozens, not thousands. Estimates put the number at something like 10 to the 500th. That's a 1 followed by 500 zeros. Each compactification corresponds to a different vacuum state, a different low-energy configuration of the string theory fields, and each vacuum state has different properties, different particle masses, different force strengths, different cosmological constants. This vast collection of possible vacuum states is called the string theory landscape, and it's one of the most contentious ideas in modern physics. The landscape is not a physical place, it's a mathematical space, a way of organizing all the possible vacuum states that string theory allows. Each point in the landscape represents a different universe, a different set of physical laws. And if you combine the landscape with eternal inflation, you get level 2 multiverse in its most dramatic form. As eternal inflation produces bubble after bubble, each bubble could settle into a different point in the landscape. Each bubble could end up with different physics. Our universe, the one we observe, is just one bubble with one particular set of vacuum state parameters. Other bubbles exist with different parameters, and because there are 10 to the 500th possible states, and eternal inflation produces infinitely many bubbles, every point in the landscape gets realized. Not just the ones that look like our universe, all of them, including vast numbers of universes where the laws of physics are so different from ours that structure never forms. Universes where the cosmological constant is so large that space expands too fast for galaxies to assemble. Universes where the strong force is so weak that atomic nuclei fall apart. Universes where electrons are so massive they immediately collapse into their nuclei. Dead universes, lifeless universes, universes that blink into existence and expand forever without ever producing a single star. This is where the anthropic principle comes in. The anthropic principle is not a physical law. It's a selection effect. It says that we should not be surprised to find ourselves in a universe capable of supporting observers, because if the universe were not capable of supporting observers, we would not be here to notice. It's circular reasoning that happens to be logically airtight. And in the context of a level 2 multiverse, it provides an explanation for why the physical constants in our universe seem so finely tuned. The cosmological constant, the amount of dark energy driving the accelerated expansion of space, is measured at about 10 to the negative 122 in natural units. That's absurdly small. Quantum field theory predicts it should be something like 10 to the negative 3, about 120 orders of magnitude larger. If the actual value were anywhere close to the prediction, space would expand so fast that atoms could not hold together, let alone galaxies, let alone stars and planets and life. The fact that the cosmological constant is so small is one of the biggest fine-tuning puzzles in physics, and for decades nobody had a good explanation. The multiverse offers one. If there are 10 to the 500th universes, each with a different value of the cosmological constant, then some of them, by pure chance, will have values small enough for structure to form. Most universes will not. Most will be lifeless. But in the tiny fraction of universes where the constant is small enough, galaxies form, stars ignite, planets coalesce, and eventually, observers appear. We find ourselves in one of those rare universes, not because the constant was tuned by some external agent, but because we could not exist in a universe where it was not tuned. It is a statistical argument, and it is deeply unsatisfying to a lot of physicists because it replaces a mechanistic explanation with a probabilistic one. It says the universe looks the way it does not because some deep principle requires it, but because we won the cosmic lottery. We live in a bubble where the numbers happen to be right. Other bubbles exist where the numbers are wrong, but nobody is there to complain about it. The debate over the anthropic principle is fierce. Some physicists, including Steven Weinberg, who used anthropic reasoning to predict the rough value of the cosmological constant before it was measured, argue that it is a legitimate scientific tool. Others, including many particle physicists who have spent their careers searching for deeper explanations, argue that it is giving up, that it is replacing the search for a mechanism with a shrug and a statement that we are lucky, that it turns physics into environmental science, where the laws we observe are contingent facts about our local bubble, rather than fundamental truths about reality. Both sides have a point. The anthropic principle is logically sound. It does explain certain observations that are otherwise baffling, but it also closes off lines of inquiry. If you accept that the cosmological constant is just a random draw from the landscape, you stop looking for a reason why it has the value it does, and maybe there is a reason, a symmetry, a principle, a mechanism we have not discovered yet. The anthropic explanation says we will never find that mechanism because there is no mechanism to find, just statistics. Level 3 multiverse is different. This one comes from quantum mechanics, specifically from the many worlds interpretation. In standard quantum mechanics, when you measure a particle, the wave function collapses and you get a single definite outcome. Before the measurement, the particle was in a superposition of all possible states. After the measurement, it's in one. The many worlds interpretation, proposed by Hugh Everett in the 1950s, says the collapse is an illusion. The wave function does not collapse, it keeps evolving, but the universe splits. Every time a quantum measurement happens, every possible outcome is realized in a different branch of the wave function. You, the observer, split along with the universe. One copy of you sees outcome A, another copy sees outcome B. Both versions are real, both exist in parallel in different branches of the quantum multiverse. And because quantum measurements are happening constantly, everywhere, at every scale, the universe is splitting into an unimaginably vast number of branches every fraction of a second. Tegmark argued that level 3 adds nothing qualitatively new. All the branches exist within the same mathematical structure, described by the same Schrödinger equation, governed by the same laws. The only thing that varies is which outcomes you happen to observe. In that sense, level 3 is less radical than level 2, where the laws themselves can differ. But level 3 is psychologically disturbing in a way level 2 is not. Level 2 says there are other universes out there far away with different physics. Fine, you will never see them. You will never interact with them. They might as well not exist as far as your daily life is concerned. Level 3 says there are other versions of you, right here, now, living different lives because a quantum measurement went the other way. A version of you who chose a different career, a version who never met the person you married, a version who died in a car accident you narrowly avoided. All of them real, all of them conscious, all of them convinced they are the one true version. And the number of branches is so large, growing so fast, that every possible history consistent with quantum mechanics is being lived out by some version of you somewhere in the multiverse. This is philosophically nightmarish. It suggests that free will, if it exists at all, is meaningless, because every choice you could make is being made by some version of you in some branch. It suggests that probability loses its usual meaning because all outcomes happen, and the probabilities just tell you the relative weights of the branches. It raises questions about identity, continuity, and what it means to be you when there are countless other yous diverging from your timeline every instant. And yet the many worlds interpretation is taken seriously by a significant fraction of physicists because it solves the measurement problem, the question of how and why wave function collapse happens. By denying that collapse happens at all, the math is clean. The theory is deterministic. The only cost is accepting that reality is vastly larger and stranger than it appears. Level 4 is the most radical. This is the idea, championed by Tegmark, that every mathematical structure that is consistent and logically self-contained corresponds to a real universe. Not just universes with different physical constants or different quantum outcomes. Universes with entirely different mathematical laws. A universe where time has two dimensions. A universe where space is discrete rather than continuous. A universe governed by different equations, different symmetries, different logic. If a mathematical structure is coherent, it exists somewhere, and conscious observers within that structure perceive it as physical reality. This is the mathematical universe hypothesis, and it is more philosophy than physics because it is not clear how you would ever test it. But Tegmark argues that it is the natural endpoint of the multiverse hierarchy. If you accept level 1, you're already accepting that distant regions with different initial conditions exist. If you accept level 2, you're accepting that different physical laws exist. If you accept level 3, you're accepting that all quantum outcomes exist. Level 4 just takes the next step and says all mathematical possibilities exist. At that point, the distinction between mathematics and reality dissolves. Reality is mathematics. The universe we observe is just one structure in the space of all possible structures, and that space is infinite. Now, here is the problem. The multiverse in any of its forms is extraordinarily difficult to test. Level 1, fine. We cannot see those distant duplicates, but we can measure the curvature of space and the distribution of matter to constrain whether the universe is infinite. Level 2, harder. We cannot see other bubbles because the space between them is expanding too fast. But some theorists have proposed that if two bubbles collided in the past, the collision might leave a signature in the cosmic microwave background. A circular discontinuity, a bruise in the sky. Several groups have searched for these signatures. None have been found. That does not mean level 2 is wrong. It just means either we have not looked carefully enough or our bubble has not collided with another one, which is statistically likely given the vast distances involved. Level 3 is testable in principle because it makes predictions about the statistics of quantum measurements, but those predictions are subtle and hotly debated. And level 4 is not testable at all because it encompasses all possible mathematical structures, including ones we could never observe or even conceive of. This lack of testability drives some physicists to despair. Science works by making predictions and comparing them to observations. If a theory predicts something that cannot be observed, even in principle, then is it science, or is it metaphysics? The question is not settled. Proponents of the multiverse argue that it is a prediction that falls out of well-tested theories like inflation and quantum mechanics. We did not invent the multiverse to solve a problem, it emerged from the equations, and if the equations are right, which all the evidence so far suggests they are, then the multiverse is real whether we like it or not. Critics argue that a prediction you cannot test is not a prediction, that the multiverse is an elaborate excuse for giving up on finding deeper explanations, that it is a failure of imagination disguised as a success of theory. Both sides are dug in, both have good arguments, and the debate shows no signs of resolving anytime soon. There is also the measure problem. If eternal inflation produces infinitely many bubbles, and you want to calculate the probability of observing some particular property in a randomly chosen bubble, you run into trouble. Infinity divided by infinity is not a well-defined number. You have to impose some kind of cutoff, some way of counting the bubbles, to make the calculation meaningful, but different cutoffs give different answers. Wildly different answers. The probabilities depend on how you choose to measure the multiverse, and there is no consensus on which measure is correct. Some measures predict that we should observe a much larger cosmological constant than we do. Others predict we should see different types of particles. None of them cleanly reproduce all the observations without additional assumptions. This is a serious technical problem. It means that even if the multiverse exists, extracting testable predictions from it is fiendishly difficult. You cannot just say anything goes. You need a way to calculate what is likely and what is not. And right now, we do not have a reliable way to do that. Despite these problems, the multiverse has become a fixture of modern cosmology. Not because it is proven, but because it is hard to avoid. Inflation solves so many problems, matches so many observations, that most cosmologists believe it happened. And if inflation happened once, the math says it should be happening eternally, producing bubbles. String theory is the leading candidate for a theory of quantum gravity, and the landscape is a generic feature of string theory, not something you can easily remove. Many worlds is one of the cleanest interpretations of quantum mechanics, with no ad hoc collapse postulate. The multiverse is not something anyone wanted, it is something the theories give us whether we want it or not. And that puts physics in an uncomfortable position. The theories that work best, that explain the most data, that require the fewest arbitrary assumptions, all point toward a reality vastly larger than the universe we can see. A reality where our observable universe is one tiny bubble in an infinite froth, where the laws we observe are local bylaws, not universal truths, where the fine-tuning that makes life possible is a selection effect, not a miracle. Some physicists have embraced this. Brian Greene, in his popular writings, catalogues a dizzying array of multiverse types. Inflationary multiverses, brain multiverses from higher dimensional string theory, cyclic multiverses where universes bounce and reboot over and over, landscape multiverses from the string vacuum states, quantum multiverses from many worlds, simulated multiverses where our reality is a computation running on some higher level substrate, and more. Each has its own theoretical motivation. Each extends the concept of reality in a different direction. and each, in its own way, suggests that the universe we see is a fragment of something incomprehensibly larger. Others have recoiled. Paul Steinhardt, one of the original architects of inflationary theory, has become one of its harshest critics, arguing that eternal inflation and the multiverse it produces make the theory unfalsifiable and therefore unscientific. Lee Smolin has argued that the landscape and anthropic reasoning represent a dead end for physics, a retreat from the goal of explaining why the laws are what they are. George Ellis has warned that without testability, the multiverse risks becoming a kind of pseudoscience, a mathematical fantasy disconnected from empirical reality. The debate is more than academic. It cuts to the heart of what science is and what it is trying to do. Is the goal to explain everything we observe in terms of deeper principles? Or is the goal to build models that match the data, even if those models include elements we can never directly test? Is the multiverse a bold extension of our best theories into uncharted territory? Or is it a signal that those theories have overreached, that we are confusing mathematical possibility with physical reality? There are no easy answers. The multiverse is not going away. It is baked into inflation. It is baked into string theory. It is baked into many worlds. And until someone comes up with a better framework that explains the data without invoking multiple universes, the multiverse is here to stay. But here is what the multiverse does, whatever its ultimate truth value. It forces us to reconsider what we mean by the universe. For centuries, the universe was everything, the totality of existence, the stage on which all events occur. The multiverse says that stage is bigger, much bigger, that what we call the universe is just one room in an infinite mansion, one pixel in an endless image, one note in an eternal symphony. And that realization, even if it turns out to be wrong, is philosophically and scientifically profound. It changes the questions we ask. It changes how we think about our place in the cosmos. It changes the meaning of fine-tuning, the meaning of the laws of physics, the meaning of existence itself. If the multiverse is real, then the Big Bang is not the beginning. It is a beginning. One bubble nucleating in a never-ending process. The quantum foam is not the substrate our universe emerged from. It is a factory, churning out universes constantly, each with its own set of properties, each exploring a different possibility in the space of what can be. The fine-tuning we observe is not a cosmic mystery. It is a statistical inevitability. In an infinite multiverse, every possible configuration gets realized. We observe this particular configuration because we could not exist to observe any other. And the laws of physics, those deep principles we have been trying to uncover for centuries, might not be fundamental at all. They might be contingent facts about our bubble, as arbitrary and local as the weather. That is either liberating or terrifying, depending on your perspective. Liberating because it means we do not have to explain why the cosmological constant is so small, or why the electron mass is what it is. Those are just the values that happen to hold in our bubble. Other bubbles have other values. Terrifying because it means we might never find a deeper explanation, that the search for a final theory, a single elegant framework that explains everything, might be doomed, not because such a theory does not exist, but because it describes the multiverse, not just our universe. And the multiverse is too large, too diverse, too fundamentally untestable for us to ever fully grasp. We are left with a map of one small region, one bubble, with no way to see the rest of the territory. And that is a frustrating place for science to end up. And yet the multiverse offers something else, a sense of scale. A reminder that the universe we observe, as vast as it is almost certainly not the whole story. That the edges of our knowledge are not the edges of reality. That the cosmic horizon we see, the boundary beyond which light has not had time to reach us, is not a wall, it is a window, a glimpse into something larger. And whether or not we ever confirm the existence of other universes, whether or not we ever detect a bubble collision or decode the string landscape or resolve the measure problem, the fact that our best theories point toward the multiverse tells us something important. It tells us that reality is strange. Stranger than we imagined. Stranger than we might be capable of imagining. And that strangeness is not a bug. It is a feature. The universe, or the multiverse, is under no obligation to make intuitive sense to creatures like us, evolved to hunt and gather on an African savanna. The fact that we can model it mathematically, that we can probe its edges with telescopes and particle colliders, That we can ask these questions at all is remarkable. And the fact that the answers are so deeply weird, so far removed from everyday experience, is not a failure. It is a testament to how far we have come. So where does that leave us? Standing at the edge of the observable universe, staring out into the cosmic foam, wondering whether the Big Bang that birthed our cosmos was unique or routine, whether the laws we observe are universal or local. Whether the fine-tuning is a clue or a coincidence, the multiverse does not answer those questions cleanly. It complicates them. It adds layers of uncertainty and speculation. But it also expands the canvas. It takes the question of origins and pushes it outward, from one universe to many, from one Big Bang to an eternal cascade. And in doing so, it raises a new question. If the multiverse exists, if other universes are constantly being born from the quantum foam, could there be evidence? Could there be signatures, fingerprints, echoes of that larger structure visible in the universe we can observe? Faint traces of bubble collisions in the cosmic microwave background, anomalies in the distribution of matter, patterns that do not quite fit the standard model but make sense if our bubble interacted with another. The search for those signatures, for any hint that our universe is not alone, is ongoing. And whether or not we find them, the search itself is pushing cosmology into new territory, forcing us to think bigger, to imagine more boldly, to confront the possibility that the universe we know, the one we have spent centuries mapping and measuring, is just the beginning of the story. We left off staring into the possibility that our universe might be one bubble among countless others, each with its own Big Bang, its own history, its own set of rules. The multiverse sitting at the edge of testability, frustrating and fascinating in equal measure. A prediction that falls out of our best theories, but one we might never confirm because the other bubbles are beyond our cosmic horizon, carried away by the expansion of space faster than light can travel. That isolation, that fundamental disconnect, is what makes the multiverse so hard to swallow for a lot of physicists. It feels less like science and more like metaphysics when you can't point a telescope at it and check whether it's really there. But there's another class of ideas, equally speculative but different in a crucial way. These ideas suggest that if something existed before the Big Bang, or if our universe is part of a larger cycle, there might be traces, fingerprints, echoes left behind in the structure of space-time or the distribution of matter, or the faint glow of the cosmic microwave background, observables, things we could, in principle, detect if we looked carefully enough and knew what we were looking for. These are the cyclic models, the bouncing universes, the cosmologies that treat the Big Bang not as the beginning of everything, but as a transition, a bounce, a reset. The latest chapter in a story that has no first page. The idea of a cyclic universe is old, ancient really. Hindu cosmology has been talking about endless cycles of creation and destruction for millennia. The Greeks played with the concept. Nietzsche had his eternal return. But the modern scientific version, the one grounded in general relativity and quantum field theory, is different. It's not philosophy. It's physics, or at least it's trying to be. And one of the most audacious versions of this idea comes from Roger Penrose, a mathematician and physicist who has spent decades thinking about black holes, space-time singularities, and the deep structure of the universe. In 2005, Penrose proposed something he himself called outrageous, a model called conformal cyclic cosmology, usually shortened to CCE. The idea is that the universe doesn't have a beginning in the usual sense. What we call the Big Bang is not the start of time, it's the transition point between two aeons, the far future of one universe mathematically connected to the Big Bang of the next. An endless sequence stretching backward and forward forever, with no first eon and no last. Just an infinite chain of cosmic epochs, each one emerging from the ashes of the one before. Here's how it works, or at least how Penrose argues it works. In the far future of our universe, long after the stars have burned out and the galaxies have dispersed, and even the black holes have evaporated through Hawking radiation, the cosmos will be a cold, dark, empty expanse, filled with nothing but photons and other massless particles drifting through space at the speed of light. No matter, no structure, no clocks ticking because there's nothing left to change. Time, in the usual sense, loses its meaning. And here's where the math gets strange. Penrose noticed that you can take that far future state and apply a mathematical trick called a conformal rescaling. You stretch or compress the metric, the mathematical object that describes distances and intervals in space-time, in a way that preserves angles but not sizes. When you do that, the far future of a dying universe and the Big Bang of a new universe become mathematically identical. The cold, empty void at the end of one aeon is, after the rescaling, indistinguishable from the hot dense state at the start of the next. The transition is smooth. There's no singularity in the traditional sense, no point where the equations blow up. Just a crossover surface where one aeon ends and another begins. This is not a collapse and rebound in the usual sense. The universe doesn't contract back down to a point and then explode outward again. That's the old cyclic model, and it has problems, entropy for one. The second law of thermodynamics says entropy always increases, and if the universe collapses and rebounds, you'd expect entropy to build up over successive cycles until eventually the whole thing grinds to a halt. Penrose sidesteps that problem by arguing that the far future state is one of extremely low entropy, not high entropy. How? Because in a universe with no matter, only massless particles, entropy as we usually define it doesn't apply. There are no particles to count, no configurations to randomize. The system is, in a weird sense, as ordered as it can be, and that low entropy state is what allows the crossover to the next aeon. The new Big Bang starts fresh, with low entropy, and the cycle continues forever. Penrose introduced the idea in 2005 and expanded on it in his 2010 book, Cycles of Time. He framed it as a solution to several cosmic puzzles. Why is the entropy of the early universe so low, far lower than you'd naively expect for a random initial state? In CCC, it's low because it's the endpoint of the previous aeon's evolution toward simplicity. Why is the universe so flat and homogeneous? Because the conformal rescaling smooths everything out across the transition. Why does inflation seem to require such finely tuned initial conditions? In Penrose's model, you don't need inflation at all. The smoothness comes for free from the cyclic structure. The idea is bold, mathematically sophisticated, and deeply controversial. Most cosmologists don't buy it. Not because it's obviously wrong, but because it makes assumptions that feel arbitrary, and because it's not clear the model actually solves the problems it claims to solve. But Penrose is not some fringe crank. He won the Nobel Prize in Physics in 2020 for his work on black holes. He's one of the most respected mathematical physicists alive. When he proposes something this radical, people listen, even if they don't agree. The big question, the one that separates CCC from pure speculation, is whether it makes testable predictions. And Penrose claims it does. He argues that massive structures in the previous aeon, specifically supermassive black holes colliding and spiraling into each other, would release enormous amounts of energy in the form of gravitational waves. Those waves would propagate through space-time, and when the aeon transitions to the next one, the waves would leave an imprint. Not in the structure of matter, because there's no matter yet, but in the geometry of space-time itself, and that imprint, Penrose suggests, would show up in the cosmic microwave background as circular patterns. Rings of slightly higher or lower temperature, centered on specific points in the sky. He calls them Hawking points, after Stephen Hawking, and he's looked for them in the data. In 2010, Penrose and a colleague named Vahe Gozadian published a paper claiming they had found evidence of these concentric circles in the data from the WMAP satellite, one of the missions that mapped the cosmic microwave background in the 2000s. The claim generated a lot of noise. If true, it would be direct observational evidence of a pre-Big Bang universe, a hint that our aeon is not the first. Other groups immediately jumped on the analysis. Several teams ran their own tests, generating simulated microwave background maps based on standard inflationary cosmology with no cyclic structure, and found that the same kinds of circular patterns showed up purely by chance. The patterns Penrose and Gozadian identified were not statistically significant. They were consistent with random noise in a universe that followed the standard Big Bang model. The claim fell apart under scrutiny. Penrose pushed back, arguing that the critics were using the wrong statistical tests, that the patterns were real and robust if you looked at them the right way. But the broader cosmology community was not convinced. As of now, the general consensus is that there is no accepted observational evidence for conformal cyclic cosmology. The model remains speculative, interesting, mathematically rich, but unproven. That doesn't mean the search is over. The cosmic microwave background is one of the richest datasets in cosmology, and we've barely scratched the surface of what it might be telling us. The Planck satellite, which mapped the microwave background with even greater precision than WMAP, has provided a flood of data that researchers are still analysing, and there are next-generation experiments in the pipeline, ground-based telescopes and balloon missions designed to measure the polarisation of the microwave background at unprecedented sensitivity. If there are echoes of a previous aeon, subtle distortions in the geometry of space-time imprinted at the moment of the Big Bang, they might show up in that polarisation data. Not as obvious smoking guns, but as faint anomalies. Patterns that don't quite fit the predictions of standard inflation. Deviations that are small, but persistent. The kind of signals that take decades of careful observation and analysis to confirm or rule out. Gravitational waves are another potential probe. The kind of gravitational waves we've detected so far with LIGO and Virgo come from relatively recent events. Black holes and neutron stars colliding in the nearby universe within a few billion light years. But there should also be a primordial gravitational wave background, ripples in spacetime generated in the first fraction of a second after the Big Bang. Inflation predicts these waves. They're a direct consequence of the exponential expansion. Quantum fluctuations in the gravitational field itself stretch to cosmic scales. Detecting them has been one of the holy grails of cosmology for decades. In 2014, a team working with the BICEP-2 telescope at the South Pole announced they'd found the signature of primordial gravitational waves in the polarization of the cosmic microwave background. The physics community exploded with excitement. Here, finally, was direct evidence of inflation. Except it wasn't. Follow-up observations revealed that the signal was contaminated by dust in our own galaxy. The so-called discovery evaporated. The search continues, but so far, primordial gravitational waves remain undetected. Now, if you're thinking about cyclic models, primordial gravitational waves get even more interesting. Because the spectrum, the distribution of wave amplitudes at different frequencies, depends on what happened during the very early universe. If the universe went through a standard inflationary phase, you get one kind of spectrum. If the universe bounced from a contracting phase, you get a different spectrum. The details depend on the specific bounce mechanism, how the transition from contraction to expansion happens, what kinds of matter and energy are present, how quantum gravity modifies the behavior of spacetime at extreme densities. But the point is that different models make different predictions, and if we ever detect the primordial gravitational wave background, if we can measure its spectrum precisely enough, we might be able to tell which model is right, whether the universe started from a singularity or from a bounce or from something else entirely. There are other cyclic models besides Penrose's. One of the most developed comes from Paul Steinhardt and Neil Turok, both serious cosmologists with long track records of contributions to inflationary theory and early universe physics. Their model, sometimes called the ekpyrotic universe, involves extra dimensions from string theory. The idea is that our universe is a three-dimensional membrane, a brain, embedded in a higher dimensional space. There are other brains out there parallel to ours, and occasionally they collide. When two brains smash into each other, the collision releases an enormous amount of energy. That energy gets dumped into both brains, heating them up, filling them with matter and radiation. From our perspective, living on one of the brains, the collision looks like a big bang, but it's not a beginning in the absolute sense. It's just the latest collision in a sequence that's been going on forever. The brains drift apart, cool down, and eventually collide again. Each collision is a new big bang. Each cycle lasts trillions of years, and because the collisions happen over and over, the universe is cyclic. No first cycle, no last cycle, just an endless series of bangs and drifts. The ekpyrotic model was proposed in the early 2000s and generated a lot of excitement because it offered an alternative to inflation. Inflation solves the horizon problem, the flatness problem, the monopole problem, all in one go. But inflation also has its own fine-tuning issues. Why does the inflaton field start in the right state? Why does it have the right potential energy curve to drive exponential expansion? Why does inflation last just long enough to solve the problems, but not so long that it wipes out all structure? Steinhardt and Turok argued that the ekpyrotic scenario could solve the same problems without invoking inflation. The collision of the branes naturally produces a hot, dense, expanding universe. The slow approach of the branes before the collision smooths out any initial irregularities. The entropy produced during one cycle dissipates into the extra dimensions, preventing the entropy build-up problem that plagued earlier cyclic models. It was a neat package. And like CCC, it made predictions. Specifically, it predicted that the primordial gravitational wave signal should be much weaker than inflation predicts. Inflation produces tensor modes, gravitational waves, at a relatively high amplitude. The ekpyrotic model predicts they should be nearly undetectable. So if we ever measure the primordial gravitational wave background and find a strong signal, ekpyrotic models are in trouble. If we find a weak signal or no signal at all, inflation has some explaining to do. Steinhardt has since become one of the most vocal critics of inflation, arguing that the theory has become so flexible, with so many free parameters and so many different versions, that it's no longer falsifiable, that it's turned into a kind of paradigm that can accommodate any observation by tweaking the details. He's proposed cyclic models as a more predictive alternative. But the cyclic models have their own problems. The brane collision mechanism relies on string theory, which is itself unproven and highly speculative. The ekpyrotic scenario makes specific assumptions about the geometry of the extra dimensions, the properties of the branes, the forces that drive them together. Change any of those assumptions and the predictions change. It's not clear the model is any less fine-tuned than inflation once you account for all the inputs, and observationally the jury is still out. We don't have the primordial gravitational wave detection yet. We don't have a smoking gun in the microwave background that clearly favours one model over the other. What we have is a collection of competing ideas, each with its own strengths and weaknesses, each waiting for the next generation of observations to either confirm or rule them out. Then there's the question of what a bounce actually looks like. Because if the universe is cyclic, if it transitions from a contracting phase to an expanding phase, you have to explain how that happens without hitting a singularity. Classical general relativity says that a collapsing universe inevitably ends in a singularity, a point of infinite density where the equations break down. To avoid that, you need new physics, quantum gravity, modifications to general relativity that become important at high densities. One approach comes from loop quantum gravity, a framework that treats space-time as fundamentally discrete, made of tiny loops woven together like a fabric. In loop quantum gravity, when you compress space-time to near the Planck density, quantum effects kick in and generate a repulsive force, a kind of quantum bounce. The collapse halts, the universe rebounds, and the transition is smooth, with no singularity. The math is complicated, the theory is still under development, but the basic picture is that quantum geometry prevents the universe from collapsing all the way to a point. It bounces instead, transitioning from contraction to expansion in a brief moment of extreme density and temperature. Loop quantum cosmology, the application of these ideas to the early universe, has been explored in detail over the past couple decades. Researchers have calculated what the bounce would look like, what kinds of observational signatures it might leave. One prediction is that the bounce would produce a specific pattern of fluctuations in the density of matter, slightly different from what inflation predicts. Those fluctuations would show up in the cosmic microwave background as a distinctive power spectrum. Measuring that spectrum precisely enough to distinguish between inflation and a bounce is hard, but it's not impossible. The Planck satellite has already put tight constraints on the shape of the spectrum, and those constraints are consistent with inflation, but don't definitively rule out all bounce scenarios. Future experiments, with better sensitivity and better control of systematic errors, might be able to tell the difference. There's also the question of what happens to information during a bounce. In a black hole, information that falls past the event horizon is, according to classical general relativity, lost forever. But quantum mechanics says information can't be destroyed. This is the black hole information paradox, one of the biggest puzzles in theoretical physics. A similar issue arises in cyclic cosmology. If the universe bounces, what happens to the information from the previous cycle? Does it get erased? Does it pass through the bounce and imprint itself on the next cycle? If information survives, you might expect to see traces of the previous universe in the structure of ours. Not detailed histories, but statistical patterns, correlations in the distribution of matter or the spectrum of fluctuations that reflect the state of the universe before the bounce. Some researchers have speculated that these correlations could show up in the cosmic microwave background or in the large-scale structure of the universe. Others argue that any information would be scrambled beyond recognition during the bounce, leaving no detectable trace. The debate is ongoing, and it hinges on details of quantum gravity that we simply don't understand yet. Another cyclic idea worth mentioning is the oscillating universe, an older concept that predated modern inflationary cosmology by decades. The basic picture is simple. The universe expands for a while, driven by the Big Bang. Eventually the expansion slows, stops, and reverses. Gravity pulls everything back together. The universe contracts, getting denser and hotter, until it reaches a point of maximum compression. Then, somehow, it bounces and starts expanding again. The cycle repeats: expand, contract, bounce, expand, contract, bounce, forever. This idea was popular in the mid-20th century because it avoided the uncomfortable question of what came before the Big Bang. There was no before. The universe was eternal, cycling endlessly. But the model ran into serious problems when physicists started taking entropy seriously. Each cycle would generate entropy, disorder, and that entropy would carry over into the next cycle. The universe would get messier over time. Stars would burn out earlier, black holes would grow larger. Eventually the cycles would slow down, the bounces would get weaker, and the whole thing would grind to a halt in a state of maximum entropy. A heat death. No more cycles. The oscillating universe in its simplest form doesn't work. You need some mechanism to reset the entropy, to restore order, or the cycles can't continue indefinitely. Penrose's CCCE tries to solve this by redefining entropy at the transition point. The ekpyrotic model tries to solve it by dumping entropy into extra dimensions. Loop quantum cosmology doesn't directly address it, though some versions suggest that quantum effects during the bounce could reset certain properties of the universe. None of these solutions are entirely convincing, and all of them require assumptions that feel a bit ad hoc. But the fact that physicists are still working on cyclic models, still refining them, still searching for ways to make them consistent with observation and thermodynamics, tells you something. The idea is too compelling to abandon. The notion that the Big Bang might not be the beginning, that the universe might be part of a larger cycle or sequence, resonates in a way that pure singularity models don't. It feels less arbitrary, less like the universe just popped into existence for no reason, and more like the universe is doing what it has always done, transitioning from one state to another in a pattern that has no start and no end. But here's the thing. Even if cyclic models are right, even if our Big Bang was a bounce or a transition from a previous aeon, it doesn't really answer the ultimate question. It just pushes it back a level. Okay, fine, the universe is cyclic. Where did the cycle come from? Why does the universe cycle instead of just existing in one static state forever? What set the whole process in motion? You've traded the mystery of the Big Bang for the mystery of the cycle, and while that might feel like progress, it's not clear you've actually solved anything. You've just moved the goalposts. The question, what existed before the Big Bang, becomes what existed before the first cycle. Or, why is there a cycle at all instead of nothing? And those questions are just as hard, maybe harder. Because now you have to explain not just one beginning, but a mechanism that produces infinite beginnings. An eternal process with no external cause. That's not necessarily a bad thing. Maybe the universe doesn't need an external cause. Maybe causality itself is something that only makes sense within a cycle, not across the boundaries between cycles. But it's unsatisfying in the way that all ultimate explanations are unsatisfying. At some point you run out of deeper answers and you're left with brute facts. The universe cycles because that's what it does. The quantum foam fluctuates because that's what quantum fields do. The multiverse produces bubbles because that's what eternal inflation predicts. Pick your stopping point. The scientific approach to these highly speculative theories is cautious and methodical. You start with the math. Does the model make internal sense? Are the equations consistent? Do they reduce to general relativity and quantum mechanics in the appropriate limits? Then you move to predictions. Does the model make testable claims about observables? Can it be distinguished from competing models? If the answer is yes, you design experiments or observations to test those predictions. If the answer is no, the model stays in the realm of speculation. Interesting, maybe even beautiful, but not yet science. Penrose's CCC has made specific predictions about circular patterns in the microwave background. Those predictions have been tested, and the results so far are negative. That doesn't kill the model, but it weakens the case. The Epoch scenario predicts a low amplitude for primordial gravitational waves. That prediction is testable, but we don't have the data yet. Loop quantum cosmology predicts specific deviations in the power spectrum of density fluctuations. Those predictions are being constrained by current observations, and future missions will tighten the constraints further. This is how science works when you're operating at the edge of what's testable. You propose a model, you extract predictions, you compare to data, and you revise or discard the model based on the results. The process is slow, it's frustrating, it requires enormous patience and intellectual honesty. And it's the only process we have that reliably gets us closer to the truth. There's also the philosophical angle, which is harder to quantify but impossible to ignore. Cyclic models change the narrative. Instead of a universe that starts from nothing, or from a quantum fluctuation that might as well be nothing, you get a universe that has always existed in some form. That might feel more satisfying to some people because it removes the need for a first cause. Or it might feel less satisfying because it denies the idea of a true beginning, a moment when something genuinely new entered existence. Different people respond differently, and those responses are shaped as much by aesthetic preferences and philosophical commitments as by the data, which is fine. Science doesn't operate in a vacuum, scientists are human. They have intuitions, biases, preferences. The goal is to design the process so that those biases don't determine the outcome. The data has to be the final arbiter. But in the early stages, when the data is sparse or ambiguous, intuition plays a role. And cyclic models appeal to the intuition that time is fundamental, that the universe is a process rather than an object, that existence is something the universe does rather than something it has. One of the strangest implications of cyclic cosmology is what it does to the arrow of time. In our universe, time has a direction. The past is different from the future. Entropy increases. Eggs break but don't spontaneously reassemble. That asymmetry is built into the second law of thermodynamics, and it's tied to the fact that the early universe had extremely low entropy. But if the universe is cyclic, what happens to the arrow of time across the transition? Does it reverse? Does it reset? In Penrose's CCC, the far future and the next Big Bang are mathematically continuous, so in some sense time just keeps flowing forward. There's no reversal. The arrow of time in the next aeon points in the same direction it did in the previous one. But in other cyclic models, especially those involving a collapse and rebound, the arrow of time becomes ambiguous. During the contracting phase, does entropy increase toward the future or toward the moment of maximum compression? If the universe bounces, does the arrow flip? Or does the bounce somehow reset the definition of future and past? These are not just abstract questions. They have implications for what kinds of structures and processes could survive a bounce. Information, causality, even the concept of events unfolding in sequence, all of these depend on the arrow of time. If the arrow is not well defined across the bounce, it's not clear what it means to talk about the previous cycle at all. There's a sense in which all of this, the cyclic models, the search for pre-Big Bang signatures, the speculation about bounces and brains and quantum geometry, is a kind of cosmological forensics. We're trying to reconstruct the history of the universe from the evidence we have today. The cosmic microwave background is a snapshot of the universe when it was 380,000 years old. The distribution of galaxies tells us how structure grew over billions of years. The abundances of light elements tell us what happened during the first few minutes. And if we're clever, if we look closely enough, maybe we can find traces of what happened even earlier. Maybe the quantum fluctuations imprinted during inflation carry information about the state of the universe before inflation started. Maybe the polarization of the microwave background encodes details of the bounce or the collision that preceded our Big Bang. Maybe the gravitational wave background contains echoes of events so far in the past that the word past stops making sense. This is the frontier, not just pushing back the timeline to earlier and earlier moments, but probing the boundary between the knowable and the unknowable, between what we can observe and what we can only infer, between physics and metaphysics. And it's worth pausing here to acknowledge just how far we've come. A century ago, we didn't know the universe was expanding. We didn't know there were other galaxies. We didn't know what stars were made of or how they produced energy. 50 years ago, we didn't know the universe was accelerating. We didn't know dark energy existed. We didn't know there was a cosmic microwave background that could be mapped in detail. Today, we can describe the state of the universe at 10 to the negative 34 seconds after the Big Bang with reasonable confidence. We can measure the temperature, the density, the composition. We can trace the evolution of structure from the first stars to the present day. We can look back in time to within a fraction of a second of the beginning and say, with evidence, this is what was happening. That is not nothing. That is an extraordinary achievement. And the fact that we're now asking whether there was something before the beginning, whether the Big Bang was a transition rather than an origin, whether there are echoes of a previous universe encoded in the structure of ours, that's not a sign that we've reached the limits of science. It's a sign that the limits keep moving. The cyclic models, the searches for pre-Big Bang signatures, the speculative proposals about bounces and brains and conformal rescaling, all of this is exploratory science. It's science at the edge, where the data is sparse and the theories are under-constrained and the risk of being wrong is high. But it's also where the biggest discoveries happen. Because if you only work on problems where the answers are obvious, you never learn anything new. The whole point of science is to venture into the unknown, to ask questions that might not have answers, to follow the evidence wherever it leads, even if it leads somewhere uncomfortable or counterintuitive or deeply strange. Cyclic cosmology is strange. It asks us to give up the idea of a first moment, to accept that the universe might be eternal in a way we've never conceived of, to consider that the Big Bang might be one event in an infinite sequence. That's a lot to swallow. But it's a possibility we have to take seriously because the alternatives, a universe that started from nothing, or from a quantum fluctuation, or from a singularity that cannot be described, are just as strange. There is no comfortable answer here. There is no version of the origin story that fits neatly into human intuition. The universe is under no obligation to make sense to us. And the deeper we probe, the clearer that becomes. So where are we? Standing at the edge of observational cosmology, looking for echoes, scanning the cosmic microwave background for circular patterns that might be the fingerprints of supermassive black holes from a previous aeon, designing detectors to catch the faint whisper of primordial gravitational waves that could tell us whether the universe inflated or bounced, building mathematical models that try to connect the far future to the distant past in ways that preserve the physics we know while extending it into regimes we don't, and acknowledging with a certain humility that we might never know for sure. The evidence might be too faint. The signals might be buried under noise. The processes that happened at the Planck scale, where quantum gravity matters, might be forever beyond our ability to probe directly. But we keep looking. We keep refining the theories. We keep building better telescopes and better detectors and better models. Because even if we never find the smoking gun, even if the echoes turn out to be too faint to hear, the act of searching is valuable. It pushes the boundaries. It forces us to think more carefully about what we mean by the beginning, by causality, by time itself. It reminds us that the universe is larger and stranger than any story we tell about it, and that strangeness is not a barrier, it's an invitation to keep asking, keep probing, keep following the math and the data into territories where the old certainties break down and new possibilities emerge. The echoes of the before, if they exist, are waiting, not in some distant galaxy, not in some exotic particle, but in the structure of space-time itself, woven into the fabric of reality at scales so small and moments so early that detecting them requires every tool we have and a few we haven't invented yet. That's the search. That's the challenge. And whether or not we succeed, whether or not we ever confirm that something existed before the Big Bang, the fact that we can ask the question, that we can frame it in mathematical language and design observations to test it, is itself a kind of answer. An answer that says the universe is comprehensible, that reality, however strange, is willing to reveal itself to those patient enough to look, and that the limits of our knowledge are not walls, they're horizons that recede as we approach them, always revealing new landscapes, new questions, new mysteries waiting just beyond the edge of what we thought was possible. We left off scanning the cosmic microwave background for echoes, building detectors to catch primordial gravitational waves, constructing mathematical models that try to connect the far future to the distant past in ways that preserve the physics we know while extending it into regimes we don't. Standing at the edge of observational cosmology, looking for fingerprints of something that might have existed before our universe began, or didn't begin, depending on which model you believe. And that ambiguity, that fundamental uncertainty about whether the Big Bang was a beginning or a transition, is not going away. Because the deeper we dig into the question of what came before, the more we realize that the question itself might be broken. Not broken in the sense of poorly phrased or imprecise. Broken in the sense that it assumes a structure, a framework of cause and effect and temporal sequence that the universe at its most fundamental level does not provide. Asking what existed before the Big Bang might be like asking what's north of the North Pole. The question sounds reasonable until you realize it's trying to apply a concept that doesn't extend that far. And that realization, uncomfortable as it is, might be the closest thing to an answer we're going to get. Let's go back to the beginning of this whole journey. 13.8 billion years ago, something happened. We call it the Big Bang, the moment when space and time and matter and energy all emerge from a state so hot, so dense, so unlike anything in our experience that our best theories struggle to describe it. For decades, cosmologists treated the Big Bang as the beginning of the universe. Not the beginning of stuff appearing in an already existing container, but the beginning of the container itself. Space and time, according to general relativity, are not separate from the universe. They are the universe, the fabric on which everything else is embroidered. And if that fabric began with the Big Bang, then there is no before, no timeline stretching backward past that point, no sequence of events leading up to it. The question, what came before the Big Bang, is asking for something that doesn't exist. A moment in time before time itself began. This is not a cop-out. This is what the equations tell us. General relativity, Einstein's theory of gravity, describes space-time as a dynamic entity that bends and stretches in response to mass and energy. And when you run the equations backward, tracing the expansion of the universe back toward its origin, you hit a singularity, a point where the density becomes infinite, the curvature becomes infinite, and the equations themselves break down. They stop giving sensible answers. Physicists call this a breakdown of the theory. It's a signal that general relativity, as successful as it is at describing the universe we observe, does not apply at the Big Bang itself. It's like trying to use a map to navigate to the edge of the map. The map is useful everywhere except the one place you're trying to go. So what do? You look for a better map, a deeper theory that extends into the regime where general relativity fails. A theory of quantum gravity. We talked about this earlier, but it's worth revisiting because it's the core of the problem. General relativity works beautifully at large scales. Planets orbiting stars, galaxies bending light, black holes warping spacetime, but it treats spacetime as smooth, continuous, infinitely divisible. Quantum mechanics, on the other hand, describes the behavior of particles and fields at tiny scales. And quantum mechanics says nothing is smooth when you zoom in far enough. Everything is grainy, fluctuating, uncertain. When you try to apply both theories at the same time, in regimes where gravity is strong and quantum effects are unavoidable, they clash. They give contradictory predictions. Infinities pop up in the calculations. The math stops working. This is the problem of quantum gravity, and it's the single biggest unsolved problem in theoretical physics. We've been working on it for nearly a century. We still don't have a complete solution. String theory is one candidate. It proposes that all particles are actually tiny vibrating strings, one-dimensional objects oscillating in 10 or 11 dimensions of spacetime. Most of those dimensions are curled up so small we never notice them, but the specific way they're curled determines what kinds of particles and forces appear in the 4 dimensions we experience. String theory is mathematically elegant. It naturally includes gravity. It unifies all the forces into a single framework. And it has passionate advocates who believe it's the best shot we have at a theory of everything. But string theory also has problems. It makes almost no testable predictions. The energy scales where its new physics would show up are far beyond anything we can reach in a particle collider. And it comes in a vast number of versions, different ways of compactifying the extra dimensions, each corresponding to a different vacuum state with different physical laws. This is the string landscape we talked about earlier, and the landscape is so large, with so many possible configurations, that extracting unique predictions becomes nearly impossible. String theory might be right. It might be the deepest description of reality we'll ever find. But after decades of work, we still don't have direct experimental evidence for it. And without that evidence, it remains a promising idea rather than an established fact. Loop quantum gravity is another candidate. It takes a different approach. Instead of replacing particles with strings, it treats space-time itself as fundamentally discrete, made of tiny loops woven together like the threads in a fabric. At large scales, the fabric looks smooth. At the Planck scale, you see the individual loops. Loop quantum gravity predicts that space-time has a minimum length scale, the Planck length, below which the concept of distance stops making sense, and it suggests that singularities, the points where general relativity breaks down, are not real. They're artifacts of treating space-time as continuous. When you account for the discrete structure, the singularities get smoothed out. The Big Bang, in loop quantum cosmology, is not a moment of infinite density. It's a bounce, a transition from a contracting phase to an expanding phase, with quantum effects preventing the universe from collapsing all the way to a point. That's an appealing picture. It avoids the singularity. It suggests the universe might be cyclic, bouncing over and over again. But loop quantum gravity also has problems. It hasn't fully unified all the forces. It makes predictions about the structure of space-time that are difficult to test. And like string theory, it's still a work in progress. A framework that shows promise but hasn't yet delivered a complete, experimentally confirmed theory of quantum gravity. There are other approaches: causal set theory, asymptotic safety, emergent gravity, each with its own mathematical structure, its own predictions, its own community of researchers working to refine the details. But as of now, in the year we're recording this, there is no generally accepted theory of everything. No unified framework that combines quantum mechanics and general relativity in a way that matches all the observations we've made and makes clear testable predictions about regimes we haven't explored yet. We're still searching, still building models, still hoping that the next generation of experiments, the next satellite mission, the next gravitational wave detection, will give us the clue we need to figure out which theory is right, or whether we need an entirely different approach that nobody has thought of yet. And here's the uncomfortable truth. Even if we do figure out quantum gravity, even if we solve the problem and build a complete theory that describes space-time at the Planck scale, it's not clear that theory will answer the question of what came before the Big Bang. Because the theory might tell us that the question is meaningless, that time is not fundamental, that it's an emergent property, something that only appears when you zoom out from the underlying quantum structure. Like temperature. Temperature is a useful concept when you're talking about large numbers of particles. It's a measure of their average kinetic energy. But it makes no sense to ask the temperature of a single particle. A single particle doesn't have a temperature, it just has motion. Maybe time is similar. Maybe at the deepest level, the universe is described by a timeless wave function, a mathematical object that encodes all possible configurations of space-time and matter without any notion of past, present, or future. And time, the flow we experience, is something that emerges when you average over a huge number of quantum possibilities, when you coarse grain, when you step back far enough that the underlying chaos starts to look like a smooth progression of events. If that's true, if time is emergent, then asking what came before the Big Bang is like asking what happened before time itself emerged. And the answer is not nothing happened, or something else happened. The answer is that the question doesn't apply. There is no before, because before is a word that requires time, and time is part of what emerged. You're asking for a sequence of events in a regime where the concept of sequence doesn't exist yet. This is not wordplay. This is a serious proposal from physicists who have spent decades thinking about the foundations of quantum mechanics and the nature of space-time. Julian Barber, a physicist who has written extensively on this, argues that time is not real at the fundamental level, that the universe is better described as a collection of possible configurations, each one existing timelessly, and the flow of time is an illusion created by the way those configurations relate to each other. Wheeler talked about a participatory universe, where observers play a role in bringing time into existence by making measurements that collapse the wave function and create a definite sequence. These are not fringe ideas. They're speculative, sure, they're not proven, but they're taken seriously by people who understand the math and they point toward a conclusion that is both deeply strange and unavoidable. The question of what came before the Big Bang might be a question our language is not equipped to ask. Now let's be clear about what this means and what it doesn't mean. It doesn't mean we should stop asking questions. It doesn't mean cosmology has hit a wall and we're done. It means we need to reframe the question. Instead of asking what happened before the Big Bang in a chronological sense, we should be asking, how does space-time emerge? What is the structure of the quantum substrate from which space-time arises? What are the rules that govern the transition from a timeless quantum state to a classical universe with a definite timeline? Those questions are harder. They don't fit neatly into the narrative framework our brains prefer, the one with a clear beginning, middle and end. But they're the questions that might actually have answers. Answers grounded in mathematics, testable through observations, connected to the physics we already understand. And here's the thing, even if we never get a complete answer, even if the ultimate origin of the universe remains forever beyond our ability to probe directly, the process of searching has already taught us an extraordinary amount. A century ago, we didn't know the universe was expanding. We thought the Milky Way was the entire cosmos. We didn't know what stars were made of or how they produced energy. Today we can describe the state of the universe at 10 to the negative 34 seconds after the Big Bang. We can measure the temperature, the density, the composition. We can trace the evolution of structure from the first stars to the present day. We can map the cosmic microwave background with such precision that we can detect temperature fluctuations of 1 part in 100,000. We can measure the abundances of light elements and confirm that they match the predictions of Big Bang nucleosynthesis to within a few percent. We can observe the acceleration of the universe and infer the existence of dark energy, a component that makes up nearly 70% of the total energy density, but that we would never have known about without pushing our observations to the edge of what's possible. That progress didn't happen because we had all the answers. It happened because we kept asking questions, kept building better instruments, kept refining the theories, kept following the data wherever it led, even when it led somewhere uncomfortable. The Big Bang model started as a speculative idea, dismissed by many physicists as absurd, a universe that started from a hot, dense state and expanded over billions of years. Ridiculous. The steady-state model, which said the universe was eternal and unchanging, was far more popular for decades. Then the evidence started piling up. The redshift of galaxies, the cosmic microwave background, the abundances of hydrogen and helium. One observation after another pointed toward a universe that had a beginning, that changed over time, that was not static. And the steady-state model, elegant as it was, couldn't explain the data. It was abandoned. Not because cosmologists wanted it to fail, but because the universe refused to cooperate. The Big Bang model won because it matched reality. That's how science works. You propose ideas, you test them, and you let the universe decide which ones survive. The same process is happening now with quantum gravity and the question of origins. We have multiple competing ideas. String theory, loop quantum gravity, other approaches. Each makes different assumptions. Each has different strengths and weaknesses. Each is waiting for the observations that will confirm or rule them out. And while we wait for those observations, we keep refining the models, calculating predictions, searching for signatures that might show up in the cosmic microwave background, or the gravitational wave spectrum, or the distribution of galaxies. The fact that we don't have a final answer yet is not a failure. It's the frontier. It's where the most interesting work happens. And the fact that the question is so hard that it requires us to rethink our most basic assumptions about time and space and causality is not a bug. It's a feature. The universe is not obligated to make intuitive sense to creatures like us, evolved to hunt and gather on an African savanna. The fact that we can model it mathematically, that we can probe its edges with telescopes and particle colliders, that we can ask these questions at all, is remarkable. There's a certain humility required here. Science has given us extraordinary power. We can split atoms, cure diseases, send probes to the outer planets, map the human genome. We've built a civilization on the back of scientific knowledge, and it's easy to start thinking that there's no problem science can't solve, no question it can't answer, given enough time and resources. But the question of ultimate origins might be one where we hit a limit. Not a temporary limit that better instruments will overcome, but a fundamental limit imposed by the structure of reality itself. If time is emergent, if the universe is quantum at its deepest level, if the transition from the quantum foam to classical spacetime is inherently probabilistic and not deterministic, then there might not be a single definite answer to the question of how it all began. There might be a range of possibilities, a wave function of histories, and asking which one is real might be like asking which outcome of a quantum measurement is real before you make the measurement. All of them. None of them. The question is malformed. That's a hard pill to swallow. We want answers. We want certainty. We want to know not just how the universe works, but why it exists at all. Why there is something instead of nothing. What set the whole process in motion. And the universe, maddeningly, might not owe us those answers. It might just be a brute fact, an irreducible starting point. Or not a starting point at all, but an eternal process with no first moment, no ultimate cause, just an infinite regress, or an infinite cycle, or a timeless quantum state from which our universe is one particular realization among countless others. None of those options feel satisfying. None of them give us the clean narrative closure we crave. But the universe is under no obligation to cater to our narrative preferences. It is what it is. And our job, as scientists, as curious beings trying to make sense of existence, is not to impose our preferred story on reality. It's to figure out what reality is actually doing and adjust our stories accordingly. And here's where the beauty comes in. Because even though we don't have all the answers, even though the ultimate question might be unanswerable in the way we'd like, the journey has been extraordinary. The models we've built, the observations we've made, the mathematical frameworks we've developed, all of it represents a triumph of human curiosity and ingenuity. General relativity is one of the most beautiful theories ever constructed. It describes gravity not as a force, but as the curvature of space-time, and it does so with a set of equations so elegant that when you see them for the first time, you can't help but feel you're glimpsing something fundamental about the structure of reality. Quantum mechanics is equally beautiful in its own way. It's strange, counterintuitive, filled with apparent paradoxes, but it works. It predicts the behavior of particles and fields with absurd precision, matching experiments to 10 or 12 decimal places in some cases. The standard model of particle physics, which describes all the known particles and 3 of the 4 fundamental forces, is a monument to decades of experimental and theoretical work. It's not the final answer. It doesn't include gravity. It doesn't explain dark matter or dark energy. It has free parameters that have to be measured rather than derived. But it's a stunning achievement nonetheless. A framework that unifies electromagnetic, weak, and strong interactions into a single coherent structure. And inflation, despite its problems, despite the criticisms, despite the lack of direct detection of the inflaton field, is one of the most successful ideas in cosmology. It explains the smoothness of the universe. It explains the flatness. It explains the origin of structure from quantum fluctuations. It makes predictions that match observations with extraordinary precision. The cosmic microwave background mapped by satellites over the past few decades shows exactly the pattern of fluctuations that inflation predicts. The scale invariant distribution, the Gaussian statistics, the adiabatic nature of the perturbations, all of it fits. That doesn't mean inflation is definitely right. It means it's the best explanation we have, and until someone comes up with a better one that explains the same data without invoking exponential expansion, inflation is the framework we work with. That's how science progresses. Not by finding final answers, but by building better and better approximations. Models that capture more of reality, that make more accurate predictions, that unify more disparate observations under a single framework. Each new model is a step closer to the truth, even if we never quite reach it. The multiverse, as speculative as it is, as frustrating as it is to many physicists because of its lack of testability, also represents a kind of intellectual honesty. It says we should take our best theories seriously and follow them wherever they lead. Inflation predicts eternal inflation and a multiverse. String theory predicts a landscape of possible vacuum states. Many worlds' quantum mechanics predicts a branching structure of parallel realities. None of these predictions were invented to solve the fine-tuning problem or to explain the anthropic coincidences. They emerged from the mathematics. And if the mathematics is right, if the theories that gave us those predictions are correct, then the multiverse is real whether we like it or not. It might be forever beyond our ability to observe directly, but that doesn't make it any less real. It just makes it harder to test. And science has dealt with hard-to-test ideas before. The existence of atoms was speculative for decades before we could observe them. The interior of the Sun was inaccessible until we developed the tools to detect neutrinos. Gravitational waves were predicted in 1916 and not detected until 2015. A century of waiting, but the prediction was correct and the patience paid off. Maybe the multiverse will be similar. Maybe we'll find a way to test it, some signature or anomaly that gives us indirect evidence. Or maybe we won't, and the idea will remain in the realm of well-motivated speculation. Either way, the fact that our theories point toward it tells us something. It tells us that the universe is bigger, stranger, more complex than we ever imagined, and that's worth knowing. The cyclic models, the searches for pre-Big Bang signatures, the speculation about bounces and brains and conformal rescaling, all of this represents the cutting edge of cosmology, the place where observation and theory meet, where the data is sparse and the stakes are high. Some of these ideas will turn out to be right. Most will probably turn out to be wrong, or at least incomplete. That's the nature of exploratory science. You propose 100 ideas and 99 of them fail, and the one that succeeds is the one that changes the field. But you can't know in advance which one it's going to be, so you have to explore all of them, test them as rigorously as you can, and let the evidence sort them out. That's messy, it's inefficient, it's frustrating. But it's the only process we have that reliably gets us closer to the truth. And the truth, whatever it turns out to be, is going to be strange. We know that already. The quantum foam, the probabilistic substrate from which space-time emerges, is not intuitive. It's not something you can visualize or hold in your mind as a coherent picture. It's a mathematical description of a regime where the usual rules break down and reality itself becomes uncertain. The multiverse, if it exists, is not a place you can visit or a collection of objects you can count. It's an infinite structure, constantly growing, encompassing every possible variation of physical laws and initial conditions. Time, if it's emergent, is not the fundamental flow we experience but a statistical property that only appears when you average over countless quantum configurations. These are not ideas that fit neatly into human intuition. They're ideas that stretch our understanding to its limits and sometimes beyond. But that's what makes them interesting. That's what makes them worth pursuing. Because the goal of science is not to confirm what we already believe. It's to discover what's actually true. And if what's actually true turns out to be weirder than anything we could have imagined, well, that's the universe's problem, not ours. Our job is to figure it out. There's also something profound about the fact that we're asking these questions at all. We're a species that evolved on a small planet orbiting an average star in an unremarkable galaxy. For most of our history, we didn't know there were other galaxies. We didn't know the Earth went around the Sun. We thought the sky was a dome with light stuck to it. And now, a few centuries after figuring out the basics of how nature works, we're probing the origin of the entire cosmos. We're asking what existed before time began. We're building mathematical models of the quantum structure of space-time. We're detecting gravitational waves from black holes colliding billions of light years away. We're mapping the distribution of matter across the entire observable universe. That trajectory, from ignorance to understanding, from mythology to mathematics, is one of the most remarkable things about the human species. We're curious. We ask questions, and we don't stop asking just because the questions get hard. We keep pushing, keep refining, keep building better tools and better theories because the alternative is to give up. And giving up is not in our nature. The limits of our understanding are not fixed. They're moving targets. A century ago, the edge of knowledge was somewhere around the formation of stars. 50 years ago, it was the cosmic microwave background. Today, it's the Planck epoch. The first 10 to the negative 43 seconds, where quantum gravity matters and our current theories break down. That boundary has been moving backward in time, getting closer and closer to the origin, for as long as we've been doing cosmology. And there's no reason to think it will stop moving. The next generation of telescopes, the James Webb's successors, will see further and more clearly. The next generation of gravitational wave detectors will pick up fainter signals, probe earlier moments. The next generation of particle colliders, if we build them, will reach higher energies, test theories in new regimes. And the next generation of theoretical physicists will come up with ideas we haven't thought of yet, approaches to quantum gravity that sidestep the problems that have stymied the current generation. The edge is moving, the horizon is receding. And every time we reach a new milestone, we find that the view from there reveals even more territory beyond. But let's also be honest about the possibility that we might not get all the way to the bottom, that there might be a fundamental limit, imposed not by our technology or our intelligence, but by the structure of reality itself, that prevents us from answering the ultimate question. If the Big Bang is a singularity in the true sense, a point where the laws of physics cease to apply, then there might be no way to probe what came before, because before doesn't exist in any meaningful sense. If the multiverse is real, and our universe is one bubble in an infinite sea, then we might be able to describe the general mechanism that produces universes, but never answer why this particular bubble has the properties it does. If time is emergent and the quantum state of the universe is timeless, then the question of origins might dissolve into a question about the structure of the wave function, and the wave function might just be a brute fact with no deeper explanation. These are uncomfortable possibilities. They suggest that there are questions we can ask that the universe is not obligated to answer, that there are limits to knowledge not because we're too dumb or too limited in our tools, but because reality at its deepest level is genuinely indeterminate, probabilistic, or simply irreducible to something simpler. If that's true, if we reach a point where we can go no further, what do we do? Do we declare victory and say we've learned as much as we can? Do we keep searching, hoping that some new insight will break through the barrier? Or do we accept the mystery and move on to other questions? There's no single answer. Different people will respond differently. Some physicists will keep working on quantum gravity, convinced that a breakthrough is just around the corner. Others will shift their focus to problems that seem more tractable, more connected to experimental data. And some will embrace the mystery, arguing that the universe's refusal to give us a final answer is itself a kind of answer. That the beauty of existence is not in having all the pieces fit together neatly, but in the endless process of discovery, the perpetual frontier, the sense that no matter how far we go, there's always more to explore. And maybe that's the real lesson here. The question of what came before the Big Bang, whether it's answerable or not, has driven some of the most profound advances in physics and cosmology over the past century. It's pushed us to develop general relativity, quantum mechanics, particle physics, inflationary cosmology, string theory, loop quantum gravity, and a dozen other frameworks. It's motivated the construction of some of the most sophisticated instruments ever built, satellites mapping the cosmic microwave background, gravitational wave detectors stretching across continents, particle colliders accelerating protons to nearly the speed of light, all of it in service of understanding where we came from, how the universe began, what the fundamental structure of reality is. And even if we never get a final answer, even if the ultimate question remains forever out of reach, the journey has been worth it. Because the journey has taught us who we are. Curious beings in a vast, strange, beautiful universe, doing our best to make sense of it all with the tools we have. That's not a failure, that's the human condition, and it's something to be proud of. The Big Bang, whatever it was, however it happened, marked the beginning of our story. Not necessarily the beginning of everything, but the beginning of the universe we inhabit. The moment when the conditions became right for structure to form, for matter to clump together, for stars to ignite, for planets to coalesce, for chemistry to become complex enough that eventually, billions of years later, living things appeared. Things capable of looking back across the entire history of the cosmos and asking how it all started. We are, in a very real sense, the universe trying to understand itself. Atoms that were forged in the cores of dying stars, rearranged into patterns capable of thought and language and mathematics, staring back at the moment of their own origin. That's extraordinary. That's worth pausing over. Because it means the question of the Big Bang is not just an academic puzzle for physicists to solve, it's our origin story. The most fundamental narrative we have about where we came from and why the universe looks the way it does. And the answer, whatever it turns out to be, won't diminish the mystery. It will deepen it. Every time we answer a big question in science, we find that the answer opens up 10 new questions we didn't know how to ask before. When we figured out that the universe was expanding, we immediately wanted to know why. When we discovered the cosmic microwave background, we wanted to know where the fluctuations came from. When we developed inflation, we wanted to know what the inflaton field was and what happened before inflation started. Each answer is a stepping stone to deeper questions. The process doesn't end, it compounds. And that's not a flaw, That's the beauty of science. It's an infinite game. There's no final level where you beat the game and the credits roll. There's just the next level and the next and the next, each one revealing new challenges, new mysteries, new territories to explore. So where does that leave us? Standing at the edge of the knowable, staring into the quantum foam, asking whether the Big Bang was a beginning or a transition or something else entirely. Acknowledging that we might never know for sure, accepting that the universe is under no obligation to give us the satisfying narrative closure we crave, and embracing the mystery. Not as a defeat, not as a sign that we've failed, but as a reminder that reality is larger than any story we tell about it. That the edges of our knowledge are not walls but horizons. That the journey of discovery is its own reward even when the destination remains out of reach. The impossible question, the question of what existed before the Big Bang, might not have an answer in the traditional sense, but asking it has taught us more about the universe, about the nature of time and space and existence, than any other question in the history of science. And that's something. That's more than something. That's everything. The universe is strange, it's vast, it's older than we can easily comprehend and larger than we'll ever be able to see. It began, or transitioned, or emerged from a state so unlike anything in our experience that even describing it requires inventing new mathematics, new concepts, new ways of thinking about reality. And we, improbable collections of atoms on a small planet in an ordinary galaxy, have managed to piece together a story that stretches from the first fraction of a second to the present day. A story grounded in observation, tested by experiment, refined over decades of painstaking work. That story's not complete, it might never be complete, but it's ours. A monument to human curiosity, ingenuity, and the refusal to accept easy answers. The Big Bang is not the end of the mystery, it's the beginning, and the fact that we can look back at it, ask what came before, and build mathematical models to explore the question is a testament to how far we've come. The impossible question remains impossible, but asking it has made us who we are, and that, in the end, might be the only answer that matters. So here we are, 13.8 billion years after whatever happened happened, standing on a rock in space staring backward through time with instruments sensitive enough to detect the faint echo of a universe that was once smaller than a grain of sand and hotter than anything language has words for. We've traced the story from quantum foam to galaxies, from the Planck epoch to the cosmic microwave background, from inflation to stars to atoms to us. And at the end of it all, the question we started with, the question that drove this entire journey, remains stubbornly, frustratingly, beautifully unanswered. What existed before the Big Bang? Maybe nothing. Maybe something. Maybe the question itself is broken, trying to apply the concept of before to a regime where before has no meaning. Maybe time is emergent and the universe is timeless at its core, and asking what came first is like asking what's north of the North Pole. Or maybe there was a previous cycle, a bounce, another universe that collapsed and rebirthed ours. Maybe we're one bubble in an infinite multiverse, constantly budding off new universes in a process that never started and never ends. Maybe the quantum foam is eternal, fluctuating forever, and our Big Bang was just one spark in an endless cascade. We don't know, and that not knowing is not a failure. It's the edge, the frontier, the place where human understanding meets the limits of reality and discovers that the limits keep moving. Every answer we find opens 10 new questions. Every boundary we cross reveals more territory beyond. The universe is not obligated to make sense to us. It's not required to give us narrative closure or satisfying explanations. It just is. And the fact that we can probe its edges, map its history, ask these impossible questions at all, that's the real miracle, not the answers. The asking, the refusal to stop looking just because the looking gets hard. We are the universe looking back at itself, trying to understand its own beginning. And whether or not we ever solve the mystery, the search has already changed us. We are not the same species that thought the stars were holes in a dome. We are something new, something capable of staring into the quantum foam and seeing not chaos but possibility. The Big Bang might have no before, but it has an after, and we're living in it. That's not nothing, that's everything. It's